Hello there, and welcome to Drift to the Stars. I'm so glad you found your way here tonight. Maybe the day was long. Maybe your body is still carrying some of it. The weight of things said and unsaid. The small effort it takes just to get through. Or maybe you are simply the kind of person who likes to end the day with something large and quiet. Something that makes the ordinary feel briefly smaller. Either way, you are here. And that is enough. Let your shoulders drop. Feel the surface beneath you, the press of it solid and still. Take one slow breath in. Let the air go where it goes. You don't need to hold anything tonight. We are going to spend some time among the galaxies. The strange ones, the quiet ones, the ones that shouldn't exist but do. Some of them are older than we can properly imagine. Some of them are tearing apart and in the tearing making something new. Some of them are so faint they are nearly nothing, and yet they are there patient in the dark. And just before we begin, if these calm, curious explorations help you unwind, consider liking and subscribing to the channel. It helps others find their way here too, one sleepy soul at a time. Now if you're ready, let's begin. The Milky Way is not the center of anything. This is confirmed. Not the center of the solar system, not the center of the local group of galaxies, not the center of the universe. There is no center. Or rather, every point is equally central, which means the word stops meaning what we thought it meant. We built our stories around the idea of being at the middle of things. Cathedrals, maps, cosmologies, all of them placed us at the heart. But the universe keeps no such arrangement. It has no heart, no edge, no preferred address. And the Milky Way, our home, our 100 billion stars, floats in it like any other, like a leaf on a very large river. There is something in that which science calls a fact, and something else calls a relief. Not diminished, just free. Like a child who has finally stopped competing for a seat that was never assigned. The shore that believed it was the whole ocean. Some galaxies are shaped like teardrops. Not the soft kind a child draws, a sharp-ended oval, one side compressed, one side trailing into a long, faint tail. This shape is not decoration. It happens when a smaller galaxy falls too close to a larger one, and the gravity of the larger pulls harder on the near side than the far side. The small galaxy stretches. It cannot pull itself back. It falls in a long arc towards something it will never stop approaching, and the falling itself reshapes it. Astronomers call this process tidal interaction, the same word they use for what the moon does to the sea. The connection is exact. It is the same force working on the same principle, just at a scale that swallows solar systems whole. Some of those teardrop galaxies contain billions of stars, all of them being pulled in the same slow direction, none of them aware. Not a wound, not a tragedy. Just the oldest shape in physics, the arc of one thing drawn toward another. A pulled thread that still holds light. Light from a distant galaxy can travel for billions of years and still arrive. This is not a metaphor. Photons, packets of light, each one real, each one with a measurable energy, leave a galaxy billions of light years away, cross an expanding universe that is stretching the space beneath them as they go, and eventually land on a mirror, inside a telescope on a mountaintop in Chile or Hawaii, where they register as a single pixel of data. That pixel becomes a dot in an image. That image becomes a galaxy we name and catalog. The photon did not know it would make it. It had no plan. It simply moved because that is what light does. It moves until something stops it. And after a journey longer than the age of the Earth, the thing that stops it is a piece of polished glass. You could argue that the glass is just as remarkable as the journey. Or you could argue more quietly that arrival is always remarkable no matter what the distance was. Something crossed the dark to reach you. Two galaxies can pass through each other without a single star colliding. This has been confirmed by observation and verified by simulation, and it remains one of the gentlest surprises in all of astrophysics. Galaxies look dense from far away, packed with light, blazing with stars. But the stars inside are so small relative to the space between them that two galaxies can interpenetrate, completely cross through each other, like two swarms of fireflies passing in a field, and emerge on the other side with no direct star-to-star contact at all. What does collide is the vast clouds of hydrogen and dust that smash together, compress and ignite new stars by the billion. So the collision is not a destruction, it is a trigger. Chaos on the outside, creation in the middle. You would not feel a star strike you. You would only feel perhaps a sudden warmth, a new sun kindling somewhere close. Two crowds walking through each other, unchanged. There is a galaxy made almost entirely of dark matter. It is called Dragonfly 44, and it sits in the Coma cluster. And when astronomers measured how fast its stars were moving, they found those stars were moving far too fast to be held in by the gravity of the visible matter alone. Something unseen was holding it together. Dark matter, whatever it actually is, made up roughly 99% of the galaxy's total mass. The stars were almost incidental, almost decoration on something invisible. Scientists still aren't entirely sure what dark matter is. It does not emit light, does not absorb light, does not interact with the electromagnetic force at all. We know it exists because of what it does to the things around it, not because we have ever touched it or seen it. Dragonfly 44 is a galaxy that is mostly absence, held in shape by something that has no shape we can measure. A jar made entirely of what it holds. Some galaxies spin the wrong way. Most spiral galaxies rotate in a direction consistent with their overall angular momentum, the spin they inherited from the cloud they formed in, like water draining in a bowl. But some galaxies rotate counter to that expected direction, or contain large stellar streams moving in the opposite direction from the main disk. Sometimes this is the remnant of a smaller galaxy that was absorbed, a visitor whose momentum was not fully aligned, whose stars now orbit in the reverse direction, like salmon swimming upstream through a school of fish, all heading the other way. Some researchers believe these counter-rotating structures tell us about the galaxy's past mergers, like a scar that shows how the healing happened. The wrong direction turns out to be a record, not an error, not a malfunction, just a signature of every collision the galaxy has ever survived. A river inside, a river running the other way. A galaxy called the Cartwheel looks exactly like a ripple in still water. It is not a metaphor. The shape is real, a bright central hub, a wide outer ring and thin spokes connecting them all, produced by a smaller galaxy that passed through the center of a larger one hundreds of millions of years ago. The smaller galaxy hit like a stone dropped into a pond. The stars of the larger galaxy were pushed outward in a ring, a wave of compression rolling through the disk, the way a sound wave rolls through air. New stars ignited along that ring, blue and bright, because compressed gas burns. The ring is still expanding today. The stone has long since passed through and continued on its way. You are seeing the universe hold the memory of a collision, not in stone, not in scar tissue, but in the arrangement of light. The ripple that never reached the edge. Still water, still moving. There are galaxies so faint we only found them by accident. Ultra-diffuse galaxies, sometimes just called UDGs, were not discovered by pointing telescopes at them intentionally. They showed up in the background of images taken for other reasons in the wide peripheral fields of data collected, while astronomers were looking for something else entirely. They are enormous in area, some as wide as the Milky Way, but so sparsely populated with stars that they are nearly transparent. The first time someone noticed one in data, it may have looked like a smudge, an artifact, an error in the instrument. It was not an error. It was a galaxy, a real structure, gravitationally bound, ancient, just extremely quiet. Not invisible, only overlooked. There is something particular about that, the idea that large things can be missed, not because they are hidden, but because they are spread so thin they fall below the threshold of what we were looking for. What we were not seeking was still there. Some galaxies have no stars forming inside them anymore. They are finished with that work. Astronomers call them quiescent, or sometimes with a plainness that lands harder than a poem read and dead. Their gas has been used up, or stripped away, or simply stopped collapsing into new stars, for reasons that are still being studied. What remains is an aging population of stars, all of them slowly cooling, slowly reddening, slowly using up the fuel they were born with. No new suns, no stellar nurseries, no clouds of hydrogen gathering toward ignition. Just the long, slow exhale of a galaxy that has finished its main work and is now drifting toward quiet. This is not a failure. Massive, elliptical galaxies, some of the largest structures in the universe, are among the most quiescent. They made their stars early in vast bursts and have been resting ever since. Not dead, just done. An old fire still warm at the center. The oldest galaxies we can see existed when the universe was less than 1 billion years old. The universe is now about 13.8 billion years old. So these are galaxies we are seeing, as they were in what amounts to the universe's infancy, before the first % of its current age had passed. Light from those galaxies has been traveling ever since, stretched by the expansion of space until it arrives at our telescopes not as visible light, but as infrared, a longer, slower wave. You cannot see this light with your eyes. It is the kind of light you feel as warmth on your skin on a summer afternoon, and yet it carries the image of a galaxy formed before the Earth existed, before the Sun existed, before the atoms in your body had been assembled by any star at all. The James Webb Space Telescope peers into that infrared and brings those images back. Ancient, clear, astonishing in their ordinariness, they look in many ways like the galaxies we see nearby. A photograph from before your grandparents' beginning. Some galaxies flicker. Not the way a candle flickers, not randomly, not from breath. Their cores brighten and then dim over cycles that last thousands of years, driven by the feeding habits of the supermassive black hole at the center. When the black hole is actively consuming nearby gas and dust, it radiates. Enormous amounts of energy pour outward from just outside the event horizon. The accretion disk glows, jets of plasma may form, and the galaxy's center becomes the brightest thing for millions of light years. Then the fuel runs low. The feeding slows. The core dims. The galaxy enters a quiet phase. Then more gas drifts inward, and it brightens again. Scientists believe our own galaxy has done this, that the Milky Way's center was once an active quasar, blazing with a light we would have seen easily from Earth if anyone had been here to see it. Now it rests. The core is quiet. But perhaps not forever. A lamp in a window on and off for 1,000 years. A quasar at the heart of a galaxy can outshine every star in the galaxy combined. This is confirmed. A quasar, short for quasi-stellar object, is powered by a supermassive black hole consuming material at an enormous rate. The accretion disk that forms around it, the swirling in spiral of gas and dust heated to millions of degrees, releases energy that can exceed the total light output of 100 billion stars. One black hole, one disk of falling gas, and the brightness of an entire galaxy of stars multiplied. Quasars are so luminous that we can see them from the edge of the observable universe. Pinpoints of light in early universe data, easily mistaken for nearby stars. Some quasars are powered by black holes billions of times more massive than the Sun. And you are somewhere in this universe, while all that is happening small, quiet breathing slowly in a dark room. A fire so bright it made the galaxy invisible. Some galaxies are cannibals. This is the accepted term, galactic cannibalism, and it describes exactly what it sounds like. A large galaxy moving through a cluster strips stars and gas from smaller companions that pass too close. The smaller galaxy loses its outer layers first, then its core is drawn inward, and eventually the larger galaxy absorbs it entirely. The Milky Way has done this. It is doing this now, slowly consuming the Sagittarius dwarf galaxy, a small companion that has already passed through our galactic disk, multiple times each pass, stripping it thinner, scattering its stars into long streams that arc around the Milky Way like ribbons. Some of those stars are now in our neighborhood, mixed in with stars we thought were native. Some researchers believe several of the stars you see on a clear night, stars that seem entirely ordinary, arrived here from somewhere else, carried in by a galaxy, our own Galaxy 8. Not the last meal, just the most recent. A river that learned its shape from every river it swallowed. The space between galaxies is not empty. It feels like it should be. The voids between galaxy clusters are some of the largest empty-seeming spaces in the known universe, stretching for hundreds of millions of light-years. But running through that apparent nothing is a web of filaments, long threads of gas and dark matter that connect galaxy clusters like the strands of a net. This structure is called the cosmic web, and it was predicted by theory before it was confirmed by observation. The filaments are made of warm gas, some of it at temperatures of 100,000 to 10 million degrees, and they channel matter through the universe, the way rivers channel water through a landscape. Galaxies don't simply sit where they formed, they drift along these filaments, fall toward intersections, accumulate at nodes. The universe is not a scattering, it is an architecture, and the architecture was there long before any eye existed to notice it. Silk threads, no one strung, holding everything in place. There is a galaxy shaped like a penguin protecting an egg. This is its informal name. The Penguin Galaxy, given to the pair NGC 2936 and NGC 2937 by astronomers who saw in the Hubble image a spiral galaxy distorted by a close companion into a shape that looked unmistakably like a bird bending over a round, bright object. The spiral galaxy is the penguin. The compact elliptical beside it is the egg. The penguin's shape is not permanent, it is mid-distortion, its arms pulled and curved by the gravity of its companion, its nucleus displaced from center. In a few 100 million years it will look like something else entirely. But right now, at this particular moment, in a process that takes billions of years, the universe has arranged billions of stars into the outline of a bird standing watch. No one chose this. No one planned it. It simply is what physics produces when gravity bends a spiral at exactly this angle, at exactly this stage of approach. Gravity drew a bird. Gravity didn't know. Some galaxies are older than our models say they should be. The James Webb Space Telescope has found galaxies in the very early universe, just a few 100 million years after the Big Bang, that are already large, already structured, already rich with stars. By the leading models of galaxy formation, there should not have been enough time for that much mass to have gathered and ignited. The universe at that age should still have been pulling itself together. And yet, these galaxies exist. They are real data, not artifacts of the instrument, not mistakes in calibration. Some researchers believe this means the early universe formed stars far faster than expected. Others think dark matter behaved differently, then collapsed more readily, seeded structure sooner. Perhaps our models of the early universe are incomplete. The universe is not obligated to match the timeline we wrote for it. It had its own schedule, and it did not share the draft. The child who arrived already grown. A galaxy called Hoag's object is a perfect ring with nothing in the middle. Almost nothing. A small, yellowish nucleus of older stars sits at the center, surrounded by a gap of near darkness, surrounded by a ring of hot young blue stars forming at an astonishing rate. The ring is not connected to the center by spiral arms or bars. It simply floats, separate, burning blue, like a crown that has drifted free of the head it once sat on. How it formed is still debated. One theory is that a smaller galaxy once passed through the center of a larger one, the same mechanism that created the cartwheel, producing the ring as a shockwave. Another theory involves the slow accretion of gas along a particular orbital path. Scientists still aren't sure. What is certain is that the ring is real, the gap is real, and somewhere inside that yellow nucleus If you looked at the Hubble image closely enough, you could see through the gap, and in the background, just barely visible, another ring galaxy, distant and dim. A ring inside the dark. Some galaxies have two supermassive black holes orbiting each other at their centers. This happens after a merger, when two galaxies combine, each carrying its own central black hole. The two black holes sink toward the combined center through a process called dynamical friction, gradually losing energy to the surrounding stars, spiraling closer and closer. At some point, they become a true binary. Two objects, each potentially billions of times the mass of the Sun, orbiting each other at a separation of just a few light years, or sometimes less. Scientists believe they will eventually merge, producing a burst of gravitational waves, ripples in the fabric of space-time, more powerful than anything else in the observable universe. Some binary black holes may already be close enough that their merger is on cosmic timescales imminent. Right now, somewhere in a galaxy, we have probably photographed two black holes as circling each other, patient inevitable, drawing 1 millimeter closer with every orbit. Two very heavy things falling toward each other slowly. The universe contains more galaxies than there are grains of sand on every beach on Earth. This comparison has been used many times, and it still does not land properly because neither number is one the human mind can actually hold. The estimate for observable galaxies sits somewhere around 2 trillion, 2 million, with most of them too faint and too far to have ever been individually detected. The estimate for grains of sand on Earth's beaches is somewhere in the 10 quintillion range, 10 million trillion, which is much larger. So the comparison may actually understate the sand, but the galaxies win in another direction. Each one contains hundreds of billions of stars, and most of those stars have planets, and the total number of planets in the observable universe may exceed the total number of grains of sand by a factor too large to name sensibly. You are not standing at the edge of a large thing. You are standing inside something that has no edge your mind can find. Count to 1, then begin again. Some galaxies are moving away from us faster than light can cross the distance. This seems to violate the rule, nothing travels faster than light. But the rule applies to things moving through space, not to space itself expanding. The universe is not a container that things move through. It is a fabric, and that fabric is stretching. Galaxies in the most distant regions of the observable universe are being carried by that expansion at recession speeds that exceed the speed of light, not because they are moving, but because the space between us and them is growing faster than light can traverse it. This means that the light those galaxies are emitting right now will never reach us. We will never see them as they are today. We are already seeing their past, and their present is in a very specific sense permanently beyond us. The edge of what we can know is not a wall. It is a horizon that keeps pace with us no matter how fast we look. The shore that recedes as the tide comes in. There are dwarf galaxies so small they orbit ours like moons orbit a planet. Some of them contain only a few million stars, a fraction of a percent of the Milky Way's population. They are gravitationally bound to us, caught in our pull-tracing slow orbits around the larger galaxy they accompany. The Milky Way has dozens of these satellites. The large and small Magellanic Clouds are the most prominent, visible from the southern hemisphere without a telescope. Others are so faint they were only discovered in the last 2 decades, hiding in the data of wide-field sky surveys. Some may be dark galaxy remnants, once larger structures stripped to near nothing by repeated close passes. You, if you live below the equator, can step outside on a clear night and see 2 of them without any instrument at all. 2 small companion galaxies, visible as smudges above the horizon, the closest large structures to our own. They have been there every night of your life. 2 small companions always slightly behind. A single photograph revealed 10,000 galaxies in a patch of sky the size of a grain of sand held at arm's length. In December 1995, the Hubble Space Telescope was pointed at a small, deliberately blank-looking region of sky near the Big Dipper. There were no bright stars in the frame. No known objects, just a piece of sky that appeared to any ground-based telescope to contain nothing of interest. Hubble stared at it for 10 consecutive days, gathering every photon it could collect. When the image was processed, astronomers found themselves looking at nearly 10,000 galaxies, each one a distinct structure, a disk or ellipse, or irregular smear of light, each one containing hundreds of billions of stars, each one billions of light-years away. The image became known as the Hubble Deep Field, and it changed in a single picture the scale at which humanity understood itself to exist. Every blank patch of sky is full. The darkness is not absence. They looked at nothing. Nothing looked back. The nearest large galaxy to ours is Andromeda, and it is heading toward us. This is measured, not estimated, not modeled in theory alone, but confirmed through the observation of its approach velocity. Andromeda is currently about 2.5 million light-years away, and it is moving toward the Milky Way at roughly 110 kilometers per second. At that pace it will arrive, will begin to interact gravitationally in a meaningful way, in about 4 billion years. The Sun will still exist then, though it will be older and somewhat brighter, and the Earth may or may not remain habitable. No human civilization as we know it will be there to watch. And yet the collision is certain. Two galaxies, each with hundreds of billions of stars, are on a course that gravity set billions of years ago, and nothing will alter. The appointment was made before the Earth formed. We simply found the calendar. Two things that have been falling toward each other since before you began. When Andromeda and the Milky Way eventually merge, it will take over 1 billion years. Not the approach, the merger itself. Galaxy collisions are not events. They are processes stretched across timescales that make human history look like a single breath. The two galaxies will first interpenetrate, passing through each other, their stars moving like two swarms of fireflies crossing in a field. Then gravity will pull them back. They will pass through each other again and again, each pass bringing them closer, until eventually, after repeated crossing, after the gas has compressed and ignited billions of new stars, after the shapes have been distorted beyond recognition, they will settle into a single larger structure. Astronomers already have a name for what they expect it to become. Milkomeda, a merged elliptical galaxy, quieter than either parent, no longer forming stars at any great rate, just drifting in the expanded universe with its trillion suns, calm after the longest storm. Two rivers, eventually the same water. The collision of Andromeda and the Milky Way will produce no sound. This is not a limitation of distance. It is a property of space itself. Sound is a pressure wave. It requires a medium, molecules bumping into molecules, compression and expansion, rippling through matter. Space between stars is not empty, but it is so extraordinarily thin that pressure waves cannot propagate through it in any way a human ear could register. The gas clouds that collide during a galaxy merger compress and ignite, releasing energy equivalent to billions of nuclear explosions per second, and all of it happens in complete silence. Not the silence of a quiet room where your ears still register the hum of air in ducts, the faint percussion of your own heartbeat. A different silence. A silence that is not the absence of sound, but the absence of the possibility of sound. The largest event in the local universe's future will happen without a single note. Two galaxies will become one, and nothing will hear it. The loudest thing that ever happened quietly. After the merger, the night sky will blaze with new stars. When the gas clouds of two galaxies collide, the compression is enough to trigger star formation on a massive scale. A starburst, billions of new suns, igniting in the space of a few 100 million years, which is brief by galactic standards. In the merged galaxy of Milkomeda, this burst of creation will light the sky with stars so numerous and so young that the night from any surviving planet would look almost white at its center. Astronomers have watched this process in other merging systems, the Antennae galaxies, the Mice galaxies, the Whirlpool and its companion. Each one shows the blue arc of new stars, tracing the compression wave. The chaos does not destroy. It manufactures. Every collision the universe has ever arranged has produced more light than was there before. Destruction and creation in this context are the same gesture seen from different distances. Chaos as the oldest form of generosity. Galaxies cluster together in groups held by gravity, and those clusters form walls across the universe. Our own Milky Way belongs to a small group, the local group, containing about 50 galaxies, most of them dwarfs, with Andromeda and the Milky Way as the two dominant members. That local group is part of a larger structure called the Virgo supercluster, which is itself part of an even larger superstructure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea contains roughly 100,000 galaxies and spans about 500 million light-years. It was only mapped in 2014, when a team of astronomers traced the flow of galaxies through space and found they were all moving gently toward a single gravitational basin. We live inside that basin. We are part of Laniakea the way a raindrop is part of a watershed, one small thing moving with everything else in the same slow direction. 500 million light-years of home. The largest known structure in the universe is a filament of galaxies over 10 billion light-years long. It is called the Hercules Corona Borealis Great Wall, and it is so large that light crossing it from end to end would take longer than the current age of the universe has existed, which creates an immediate problem. If the universe is 13.8 billion years old, how does a structure 10 billion light-years across exist? Structures need time to form under gravity, and the standard models of cosmology suggest there has not been enough time for something this large to assemble. Some researchers question the statistical methods that identified it. Others think it represents a genuine challenge to our understanding of how the large-scale structure of the universe developed. It may be real. It may be a question still in the process of becoming an answer. Either way, the universe has produced something that does not fit neatly into the story we have been telling about it. Something too large for the time it had to grow. The observable universe is about 93 billion light-years across. This number requires a moment. Light travels at about 300,000 kilometers per second, fast enough to circle the Earth 7 times in a single second. At that speed, crossing the observable universe would take 93 billion years. And yet the universe is only 13.8 billion years old. The reason the observable universe is larger than the time light has had to travel is the expansion of space. The regions we can see today were much closer when their light first departed. Space has stretched since then, carrying those regions further away, so that the light we are now receiving was emitted from points that are now much further than the distance it traveled. The numbers do not contradict each other. They describe a universe that is expanding faster than intuition expects. You are at the center of a sphere of knowable space, 93 billion light-years wide, not because you are central, but because observation always begins where the observer stands. A bubble that grew while you were inside it. Beyond the edge of the observable universe, space continues, but we will never know what is there. The observable universe is not the whole universe. It is the part of the universe from which light has had time to reach us. Beyond that, boundary space almost certainly extends further, perhaps infinitely further. Other galaxies exist out there, moving away from us at speeds greater than light, unreachable not just in practice but in principle. No signal we could send would ever arrive. No light from those regions will ever reach us. They are not hidden behind a wall. There is no wall. They are simply beyond the horizon of causality, places that exist that have stars and gas and perhaps planets, but that are permanently outside every conversation we could ever have with the universe. The observable universe is what we can know. The rest is what is. The map ends. The territory does not. Some galaxies formed so early that they should not yet contain the heavy elements needed to make planets, and yet they do. In the very early universe, only hydrogen, helium, and trace amounts of lithium existed. The heavier elements, carbon, oxygen, iron, silicon, all the material needed to build rocky planets and organic chemistry, had to be forged inside stars and scattered by supernovae. That process takes time. Stars must be born, live, and die before the next generation of planets can form around the heavier elements they leave behind. But some early galaxies appear to contain more heavy elements than this timeline allows. Either star formation ran faster and hotter in those early environments than our models predict, or some process we have not yet identified was seeding the early universe with complexity ahead of schedule. The universe seems to have been in a hurry in its youth to make the ingredients for everything that came later. The recipe was ready before the kitchen was built. A galaxy called IC 1101 is so large it would swallow the space between us and Andromeda whole. IC 1101 is the largest known galaxy, a giant elliptical sitting at the center of a galaxy cluster about 1 billion light-years away. Its diameter is estimated at about 6 million light-years. The Milky Way is roughly 100,000 light-years across. The distance between the Milky Way and Andromeda is about 2.5 million light-years. IC 1101 would contain all of that, our galaxy. It contains roughly 100 trillion stars. Not billions, trillions. A 1 followed by 14 zeros. If the Sun were a grain of sand, the Milky Way would be a beach a few kilometers long. IC 1101 would be a coastline. It is thought to have grown this large through repeated mergers consuming galaxy after galaxy over billions of years, adding each one to its mass the way a river adds tributaries. The largest known thing, still growing. There are regions of space where almost no galaxies exist at all. These are the cosmic voids, vast, roughly spherical regions that can span hundreds of millions of light-years, containing almost no visible matter. The largest known void, the Botes void, is about 330 million light-years across. If the Milky Way were at its center, the nearest neighboring galaxy would be so far away that ancient human civilizations would have looked up and seen in every direction only darkness. No smudge of Andromeda, no Magellanic clouds, just black. Astronomers once found only 60 galaxies inside the Botes void when they expected to find thousands. The void is not entirely empty, there are faint galaxies scattered through it, but it is emptier than the universe's average density by a factor that is difficult to hold. Not a hole, not a wound in the universe. Just a place where the web stretched thin and matter followed the threads towards somewhere else. A room so large its walls are invisible. These voids are not empty by accident. They were made by the same force that made everything else, gravity. In the very early universe, matter was distributed almost uniformly, with only tiny fluctuations in density regions, fractionally more dense, regions fractionally less. Over hundreds of millions of years, gravity amplified those differences. Matter in the denser regions attracted more matter. Matter in the sparser regions was pulled away. The dense regions became filaments, then clusters. The sparse regions became voids, growing emptier as their matter drained outward toward the surrounding walls. The voids are the negative space of the universe's architecture, defined not by what is in them, but by what left. The universe sorted itself over billions of years into something that looks on the largest scales like the inside of a foam or a sponge, all surface, all connection with emptiness at the center of each bubble. What left is what made the shape. The universe's large-scale structure looks from very far away like a web of soap bubbles. This is not a poetic approximation, it is how cosmologists describe it, and the visual comparison is close enough to be useful. Galaxy clusters sit at the intersections where bubble walls meet. Filaments of galaxies run along the edges between bubbles. The flat sheets of galaxies span the bubble walls themselves, and the interiors of the bubbles, the voids, contain almost nothing. This structure, called the cosmic web, emerged from quantum fluctuations in the very first moments after the Big Bang fluctuations. So small, they were smaller than an atom, amplified by 13 billion years of gravitational attraction into the largest architecture in existence. The universe began as noise. The noise became structure. The structure became everything. And the whole of it, every galaxy, every void, every filament, fits inside a geometry that a child can recognize from a kitchen sink. The universe organized itself into something you have seen before. Every intersection of the cosmic web holds a galaxy cluster. These intersections, called nodes, are the densest places in the universe, where filaments from multiple directions converge, where gravity has been pulling matter from vast distances for billions of years. Galaxy clusters at these nodes can contain thousands of individual galaxies, all bound together, all moving within a shared pool of hot gas that glows in X-rays, all embedded in a dark matter halo that outweighs the visible matter by a factor of 5 or more. Some clusters are so massive that they bend light, acting as gravitational lenses, bending and magnifying the images of galaxies behind them, producing rings and arcs and multiple images of the same distant galaxy. The cluster does not mean to do this. It simply has mass and mass curves. Space and curved space bends the path of light, the way a glass bends the path of a beam. The universe uses its own weight as a lens. The heaviest things became the clearest windows. Radio galaxies shoot jets of plasma millions of light years into the surrounding space. These jets emerge from the poles of a supermassive black hole. Two narrow beams of charged particles, accelerated to nearly the speed of light, launched in opposite directions from just outside the event horizon. They do not disperse quickly. They travel collimated and fierce, for distances that dwarf the galaxy that produced them, sometimes stretching 10, 20, even 50 times the diameter of the host galaxy, before finally spreading into vast lobes of glowing gas. The mechanism that focuses them so precisely is still being studied. Something about the magnetic fields threading the accretion disk, something about the rotation of the black hole itself, shapes those two beams into the most directional structures in the universe. A galaxy the size of the Milky Way, producing jets that extend for millions of light years in each direction, looks in radio images like a tiny seed with two enormous wings. The seed barely visible, the wings everything. Two beams aimed at nothing, arriving nowhere. Those jets can be longer than the distance from Earth to the nearest star, multiplied 1,000,000 times over. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. 1,000,000 times that distance is 4 million light-years. Some radio galaxy jets exceed even that. The largest known, produced by a galaxy called Alcyoneus, extends roughly 16 million light-years from end to end. 16 million light-years. The Milky Way is 100,000 light-years across, which means the jet of Alcyoneus is 160 Milky Ways, laid end to end. And it is a single structure, not a collection of objects, not a string of separate galaxies, but one continuous stream of plasma fired from a single point and sustained across a distance that cannot be walked in any meaningful sense of the word. What produces it is a black hole. What shapes it is magnetism. What sustains it is the rotation of spacetime itself, wound tight around a spinning mass. One black hole, one stream, longer than imagination runs. Some galaxies are lensed by gravity. A cluster in front bends the light of a galaxy behind it into arcs and rings. This effect, called gravitational lensing, was predicted by Einstein before it was ever observed. He calculated that mass curves spacetime, and that light follows the curvature of spacetime, and therefore a sufficiently massive object placed between a light source and an observer would bend the light around it, acting as a lens. The first confirmation came in 1919, during a solar eclipse, when stars near the edge of the sun appeared shifted from their true positions. Since then, astronomers have found lensing at every scale, from individual stars lensing background stars, to galaxy clusters producing complete Einstein rings, perfect circles of light from a galaxy directly behind the lens. These rings are among the most beautiful images in astronomy, a galaxy turned into a halo by the gravity of something between us and it. The universe bending its own light to show us further. Gravitational lensing lets us see galaxies that would otherwise be too faint to detect. A galaxy cluster, acting as a lens, does not just distort the images of background galaxies, it also magnifies them. The same physics that bends the light also concentrates it, the way a magnifying glass concentrates sunlight. This means that some of the most distant, faintest galaxies ever observed have only been seen because a cluster happened to sit between them and us, amplifying their light by factors of 10, 20, sometimes 100. The cluster is not doing this deliberately. It is simply massive, but the effect is that the universe has placed its own telescopes in the sky, natural lenses of dark matter and hot gas scattered across the cosmos, each one revealing something that would otherwise remain permanently invisible. Astronomers plan their observations around these lenses, now pointing their instruments at known clusters and waiting for whatever the cluster has magnified behind it. The universe hid something and used its own weight to show it. The light we catch from the most distant galaxies left before the Earth existed. The Earth is about 4.5 billion years old. The most distant galaxies we observe, those found by the James Webb Space Telescope in the very early universe, emitted the light we are receiving now, when the universe was only a few 100 million years old. That light has been traveling for over 13 billion years. The Earth did not yet exist when that light departed. The Sun did not yet exist. The atoms that would eventually form our solar system were still inside older stars, not yet scattered by supernova. And yet the light kept moving. It crossed whatever existed in the early universe, denser, hotter, stranger than now, and it is arriving today at a telescope we built on a planet that formed billions of years after its journey began. We are the destination that didn't exist when the message was sent. A letter posted before the address existed. Some of those distant galaxies no longer look the way we see them. Time has already changed them. What we observe when we look at a galaxy 13 billion light-years away is not that galaxy as it is now. It is that galaxy as it was 13 billion years ago, an image preserved in light sent toward us before our solar system formed, arriving now like a photograph from a past so deep it has no human reference point. The galaxy we are seeing may have since merged with another. It may have consumed a dozen companions. Its star formation may have ended entirely. It may have become a vast quiet elliptical drifting in a cluster, unrecognizable from its young chaotic form. We will never know. The light that shows us its current state will not arrive for another 13 billion years. We are always seeing the past. Every telescope is a window into what was, not what is. We are watching something that has already become something else. The universe itself is expanding, and has been since the first fraction of a second. This expansion is not a galaxy moving through space the way a comet moves through the solar system. It is space itself growing every point, moving away from every other point, not from a center but uniformly everywhere at once. A useful image is a raisin bread rising in an oven. Every raisin moves away from every other raisin, not because any raisin is the center, but because the bread between them is expanding. At very large scales, this is what is happening to the universe. The galaxies are the raisins. The space between them is the bread. And the oven has been on since a moment so close to the beginning that the laws of physics as we know them may not have applied yet. We live inside the rising. We always have. We cannot step outside to watch from a distance. There is no outside. The bread that has been rising since before bread was a word. This expansion means galaxies are not moving through space so much as space is growing between them. The distinction matters. When astronomers measure the recession velocity of distant galaxies, the speed at which they appear to be moving away from us, those velocities are not velocities in the usual sense. The galaxy is not accelerating away the way a rocket accelerates. The space between us and the galaxy is simply increasing, carrying the galaxy with it. A helpful way to feel this: imagine two dots on the surface of a balloon, and the balloon is being inflated. Neither dot moves across the surface of the balloon, but the distance between them increases as the balloon grows. The galaxies are the dots. The balloon is the universe. And the question of whether anything is truly moving is one that requires you to agree first on what it means to move. In a universe where space itself has a shape and a history, the question is genuinely open, still and yet receding. Some scientists believe the expansion is accelerating, pushed by something called dark energy. In 1998, two independent teams of astronomers measuring distant supernovae expected to find that the expansion of the universe was slowing down. Gravity should have been pulling things back, applying brakes. Instead, they found that the most distant supernovae were dimmer than expected, which meant they were further away than expected, which meant the expansion was speeding up. The universe was not slowing under gravity, it was accelerating. Something was pushing it apart. That something was named dark energy, not because anyone knows what it is, but because the name acknowledges both its reality and our ignorance. Whatever it is, it appears to be a property of space itself, present everywhere, constant in density, unchanged by expansion. It does not dilute as the universe grows. It grows with it. The more space there is, the more dark energy there is, the faster space expands. A force that feeds on the room it makes. Dark energy, if it exists as understood, would make up roughly 2/3 of everything in the universe. The remaining third divides into dark matter, about 27%, and ordinary matter, everything we can see, touch, or measure directly, at only about 5%. Every star, every planet, every galaxy, every atom of everything that has ever been named or photographed or held in a hand, all of that accounts for 5% of the universe's total content. The rest is dark. Not dark as in unknown to science, dark as in genuinely non-interacting with light, invisible in principle, detectable only through its gravitational effects, or in dark energy's case, through the shape of the universe's expansion. We live in a universe whose dominant contents we cannot see, cannot touch, and do not fully understand. The visible universe is the exception. The dark is the rule. The 5% that calls the rest a mystery. No one has ever detected dark energy directly. This is important to say plainly. Dark energy is inferred from the behavior of distant supernovae, from the shape of the cosmic microwave background, from the large-scale distribution of galaxies. The evidence that something is causing accelerated expansion is strong and consistent across multiple independent measurements. But the nature of that something remains unknown. Some researchers believe it is a cosmological constant, a fixed energy density inherent to empty space, as Einstein once proposed, and then famously called his greatest blunder, before it turned out he may have been right. Others think it is a field, like other quantum fields, that varies through space and time. Others think our model of gravity itself may be incomplete, and that what we call dark energy is really a sign that general relativity needs revision at cosmological scales. The name is a placeholder. The phenomenon is real. The explanation is still forming. A question the universe has not yet answered out loud. The universe may end not in fire, but in a slow, quiet drift apart. If the expansion continues to accelerate, the most distant galaxies will eventually recede beyond the observable horizon, moving away faster than light, their light never reaching us again. One by one, the galaxies outside our local group will vanish from the observable sky. Then, over trillions of years, stars will exhaust their fuel, and go dark. Black holes will slowly evaporate through a process called Hawking radiation, releasing their mass as faint heat over timescales so long they dwarf the current age of the universe by factors of millions. Eventually, if current physics holds, the universe will reach a state, sometimes called the Big Freeze, or heat death, maximum entropy. Minimum temperature, no gradients left for energy to flow across, no processes left to run. Not an explosion, not a collapse. Just the last ember cooling in a room that has been dark for longer than stars have existed. Not with a sound, with a stillness that was always coming. Our own Milky Way is a barred spiral galaxy. This means it has a central structure, not a round bulge, but an elongated bar of stars, thousands of light years long, running through the nucleus like a spoke through a hub. From the ends of that bar, two major spiral arms trail outward, curving as the galaxy rotates, and smaller arm segments branch between them. The overall shape seen from above would look like a slow pinwheel, flat, luminous at the center, growing fainter toward the edges, the arms traced in the blue light of young stars and the pink glow of star-forming nebulae. We cannot see this shape from where we sit. We are inside it, embedded 2/3 of the way out from the center, surrounded by stars on all sides, with the galactic plane cutting across our sky as the band of the Milky Way, that soft, uneven river of light, visible on dark nights, away from cities, away from the artificial glow we have laid across the ground. What you see when you look up at it is not the whole galaxy. It is the edge of the disk you are standing in. We live inside the painting we are trying to see. The sun sits roughly 2/3 of the way out from the center of the Milky Way. Not at the edge, not at the heart. Partway. In the relative suburbs, some astronomers say close enough to the galactic center that the stellar density is reasonably high, far enough that the violent environment near the central black hole does not intrude. This position may not be incidental. The inner galaxy is denser, more energetic, more prone to the kind of radiation bursts that can strip atmospheres from planets. The outer galaxy is quieter, but metal-poor, fewer of the heavy elements that build rocky worlds. The zone where we sit is in a sense temperate, not too chaotic, not too sparse. Some researchers have proposed the term galactic habitable zone. By analogy with the habitable zone around a star, a band of distance where the conditions for complex chemistry are more favorable, we are apparently in a good neighborhood. Not the most dramatic address, but a livable one. Not the center, not the edge, the place where things can last. The Milky Way takes about 225 million years to complete one full rotation. This unit of time has a name, the galactic year or cosmic year, and in those terms the Earth is about 20 galactic years old. The Sun has completed 20 laps around the center of the galaxy since it formed. The last time our solar system was in roughly this position along its orbit, the Triassic period was just beginning on Earth. Dinosaurs were new. The first mammals were small and nocturnal, and had not yet inherited much of anything. Before that, one galactic year earlier, the Great Permian extinction had just ended, the worst mass extinction in Earth's history, and life was rebuilding itself from the survivors. Each lap takes so long that the history of human civilization, everything from the first cities to this moment, occupies less than 1/10,000th of a single rotation. We have not moved far enough to notice. The dinosaurs were young the last time we were here. The center of the Milky Way is hidden from our eyes. If you look toward the constellation Sagittarius on a summer night, you are looking in the direction of the galactic center, but you cannot see it. Between us and the nucleus sit thousands of light years of dust, clouds dense and dark, absorbing the visible light from stars behind them. The center of our own galaxy is invisible in the wavelengths our eyes are built to detect. We know it is there not because we can see it, but because we can see around it, in radio waves, in infrared, in X-rays, in gamma radiation. Each of these wavelengths passes through the dust, with varying degrees of freedom, revealing different structures within the same hidden region. The infrared sky towards Sagittarius is crowded with stars our eyes will never see. The radio sky there hums with the activity of gas and magnetic fields. The X-ray sky pulses with the flares of our central black hole, waking briefly and settling again. We know where the heart is. We cannot see it beat. We know the galactic center is there. Through radio waves and infrared forms of light, our skin can feel as warmth, but our eyes cannot see. This is a remarkable fact about the human body. Infrared radiation, the same wavelength that reveals the hidden stars near the galactic center, is what you feel when you hold your hand near a warm surface without touching it. The warmth on the back of your hand on a sunny afternoon is infrared arriving from the sun. Your skin is an infrared detector. It is not a very precise one. It cannot resolve the image of a star cluster or map the structure of a molecular cloud. But the principle is the same. The photons your skin feels as warmth are cousins of the photons that carry images of the galactic center to our telescopes. When you sit in sunlight, you are detecting the same kind of light that shows us the hidden core of the Milky Way. Your body knows a kind of seeing your eyes do not. Your skin has always been reading the sky. At the very center of the Milky Way sits a supermassive black hole 4 million times the mass of the Sun. It is called Sagittarius A star, and in 2022, the Event Horizon Telescope collaboration released the first image of it. A blurry ring of orange light, the glow of hot gas, orbiting just outside the point of no return. The image took years of data collection and processing. It required 8 radio telescopes spread across the Earth. Working simultaneously, their signals combined into a single instrument with the resolving power of a planet-sized dish. And what that instrument produced was a picture of a shadow, the dark silhouette of the black hole, against the bright ring of its accretion disk. 4 million solar masses compressed into a region smaller than the orbit of Mercury, so dense that not even light traveling at the fastest speed the universe permits can pull free once it crosses the boundary. It does not announce itself. It simply holds. The heaviest silence at the center of everything we know. The central black hole of the Milky Way is not currently eating much. It sits quiet, what astronomers call low luminosity, meaning it is not actively consuming material at a rate that would make it glow the way quasars do. Occasionally, it flares a burst of X-rays or infrared, lasting a few hours, thought to be triggered by a small cloud of gas or a shredded asteroid falling past the event horizon. But these are minor events, compared to the blazing activity of active galactic nuclei in other galaxies. Our central black hole is nearly dormant. Some researchers believe it was once far more active, that billions of years ago, the Milky Way went through a quasar phase. Its center blazing with the energy of infalling gas, jets of plasma shooting outward through the halo. Structures called Fermi bubbles, 2 vast lobes of high-energy gas extending above and below the galactic plane, may be the remnant of that ancient activity. A scar from a fire long since burned down. What was once the loudest thing in the galaxy now sleeps. Around us, the Milky Way may contain more stars than there are grains of sand on all of Earth's beaches. The estimates vary somewhere between 100 billion and 400 billion stars, depending on how thoroughly you count the faint, dim red dwarfs that outnumber all other types. Red dwarfs are so small and cool that they barely glow each one, a dim ember rather than a flame, but they live for trillions of years long after the sun has died. They are the most common star in the galaxy, and they are so faint that most of them will never be visible to the naked eye from Earth. The night sky you see on a clear night shows you roughly 5,000 stars, a tiny sample from a galaxy that may hold 400 billion. The rest are there. They simply do not reach you. Not because they are too far, because they are too quiet. 400 billion fires, most of them too soft to see. Most of the stars in the Milky Way have planets. This was not known with certainty until recently. For most of human history, it was assumed or hoped but not confirmed. Then, beginning in the 1990s, planet hunting missions and ground-based surveys began finding planets around other stars, first indirectly through the wobble they induced in their host stars. Then through the tiny dimming they caused when they passed in front of them. The numbers accumulated, the patterns emerged, and the conclusion, now supported by thousands of confirmed exoplanets and statistical extrapolation across the galaxy, is that planets are not exceptional. They are ordinary. Most stars have them. Many stars have multiple. The solar system, once thought to be perhaps unique, is one arrangement among hundreds of billions of others, each one different, each one following the same fundamental physics. The galaxy is not a collection of stars. It is a collection of solar systems, and we have visited exactly one. Every star a sun. Almost every sun a world. Most of those planets are small and rocky and perhaps warm. The most common type of planet found by surveys of other star systems is smaller than Neptune but larger than Earth, a class called super-Earths or mini-Neptunes, depending on their density and composition. Many of them orbit in the habitable zones of their stars, where liquid water could theoretically exist on their surfaces. Whether any of them host life is unknown. Whether any of them host the particular chemistry that led to cells, to multicellular organisms, to anything that could look up and wonder, that is an open question, larger than any telescope has yet resolved. But the raw material is there. The distances are right. The temperatures are plausible. The universe has arranged around hundreds of billions of stars, billions of worlds, with roughly the conditions that produced on one of them everything you have ever known. Somewhere warm with the right ingredients, something waits. Some nearby galaxies are visible with the naked eye. You have seen them without knowing. On a clear night away from city light, the sky holds objects that are not stars, not planets, not clouds. They are too faint to draw attention, too steady to be anything atmospheric. They sit in the same place every night, drifting with the stars, slightly soft at the edges, slightly different in color from a pinpoint star. Two of them, the Magellanic Clouds, are visible from the southern hemisphere and have been navigational references for seafaring cultures for thousands of years. The Andromeda Galaxy is visible from both hemispheres as a faint elongated smear in the constellation of the same name. These are not tricks of the light. They are genuine other galaxies, structures of hundreds of billions of stars, hundreds of thousands to millions of light years away, visible to an unaided human eye on an ordinary night. You have perhaps looked at them without knowing what you are seeing. Most people have. You have already seen another galaxy. You may not have known its name. The Magellanic Clouds are two small galaxies that have been orbiting ours for billions of years. They are visible from the southern hemisphere without any instrument, two patches of soft light, one larger and more obvious, one smaller and fainter, positioned in the sky near the south celestial pole. To the naked eye, they look like detached pieces of the Milky Way, like clouds of light that have drifted free. They are named for Ferdinand Magellan, whose expedition documented them for European science in the 16th century, though people living below the equator had named and navigated by them for thousands of years before that. The Large Magellanic Cloud is about 160,000 light-years away. The Small is about 200,000. Each one contains billions of stars, active star-forming regions, and a complex history of interaction with our own galaxy. They are companions, old ones present in the sky of every human who has ever lived in the southern half of the world. Two old companions there every night, unnamed by most. The Andromeda Galaxy is visible on dark nights as a faint smear of light, the most distant thing the human eye can see, unaided. It sits about 2.5 million light-years away, and the light leaving your eye as you look at it has traveled that distance from its source in a galaxy of 1 trillion stars across intergalactic space through the atmosphere, through the lens of your eye, to land on your retina. 2.5 million light-years of travel, arriving in the dark of your pupil. Most people who see it for the first time are underwhelmed. It looks like a smudge, a thumbprint on the glass of the sky. It does not look like what it is. It does not look like 1,000,000,000,000 suns arranged in a flat disk 60,000 light-years across, bearing down on us at 110 kilometers per second. It looks to the naked eye like almost nothing, and it is the most extraordinary almost nothing a person can see with their own face pointed upward. 2.5 million years of travel landing in your eye. Every star you see at night belongs to our galaxy. Every single one. The night sky, as seen with the naked eye, is in its entirety a portrait of the Milky Way's local neighborhood, a sphere a few thousand light-years across, containing the stars close enough and bright enough for your eyes to resolve individually. Beyond that, the individual stars blur into the band of the Milky Way itself, too numerous and too far to separate. And beyond the Milky Way, the vast dark between galaxies and then the smudges of other galaxies, none of which resolve into individual stars for human eyes. Every point of light that has a name in a constellation, every star that sailors navigated by, every sun that ancient people told stories about, all of them ours, all of them neighbors. In the galactic sense, close enough to visit in the same way that cities on the same continent are close enough to visit. Which is to say, not easily, but within the same address. Every named star, every story, every sailor's fixed point, all one neighborhood. But the stars are not evenly spread. Between any two of them lies a distance so large that the word empty barely captures it. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. At the speed of the fastest spacecraft humanity has ever built, that journey would take roughly 70,000 years, and Proxima Centauri is our neighbor. The stars visible in the night sky range from a few light-years to a few thousand light-years distant. In every direction between every star you can name, the space is so vast that any human scale of distance, kilometers, miles, the width of a continent, loses all meaning. Not thin, not sparse, something beyond those words. Something for which human language developed no term, because human experience never needed one. The stars look close together in the sky, because the sky compresses depth. But if you could step sideways into that space, the nearest star would take your great-great-grandchildren's great-great-grandchildren to reach. Close in the painting, unreachable in the room. A galaxy is mostly empty space held together by gravity. If you took all the stars in the Milky Way and tried to pack them into a volume where they were touching, they would fit comfortably inside a sphere far smaller than the galaxy itself. The galaxy's apparent solidity, its luminous disk, its glowing core, is an illusion of scale. From far enough away, any galaxy looks continuous. Like a solid object, the way a fog bank looks solid from across a valley. But inside it is almost entirely nothing, threaded with gravity and radiation, with the occasional star like a raisin in an enormous, mostly empty loaf. This is true at every scale the universe offers. Atoms are mostly empty space. Solar systems are mostly empty space. Galaxies are mostly empty space. Matter, as it turns out, is the exception. The overwhelming texture of the universe is not substance. It is the relationship between points of substance stretched across distances that substance almost never crosses. More nothing than anything, and yet here we are. If you shrank the sun to the size of a grain of sand, the nearest star would be another grain of sand 4 kilometers away. This comparison is designed to make the emptiness feel real, and it almost works. Imagine a grain of sand on a beach. Now imagine that grain of sand is the sun, a star so large that 1,000,000 Earths could fit inside it. Now walk 4 kilometers in any direction. There, somewhere, is another grain. That is Proxima Centauri. Between them, nothing. No other grains, no dust, just 4 kilometers of bare space scaled to a model where the sun is a grain of sand. The galaxy at this scale would be a disk of sand grains spread across an area larger than Europe, each grain kilometers from its nearest neighbor. And in that enormous spread of nearly empty space, Gravity holds everything in orbit. Light crosses the distances in years, and the whole system has been turning quietly and continuously for billions of years. 2 grains, 4 kilometers, and between them nothing with a name. And yet from far enough out, the Milky Way looks solid, a flat disk of light glowing like a coal carried in the dark. This is the paradox of scale. Individually, each star is an island in a sea of nothing. Collectively, they produce something that looks from outside like matter, dense, bright, real. The Milky Way photographed from above would show a luminous bar, bright spiral arms. A thin disk fading at the edges into a soft halo. It would look like something you could set on a table. It would look like an object, and it is an object in the sense that it has mass and structure and a center of gravity. But its substance is distributed so thinly across 100,000 light-years that the word object barely applies. It is more like a weather system than a stone, a pattern of activity rather than a thing. And yet it has held together for 10 billion years, and it will hold together for billions more, because gravity does not require the things it holds to touch. A pattern of fires seen from far enough looks like one flame. Some galaxies have stellar nurseries, regions so thick with gas and dust that new stars are being born in clusters, dozens or hundreds of siblings emerging from the same molecular cloud. The Orion Nebula is the closest example to us, a region of star formation about 1,400 light-years away, visible to the naked eye as a faint smudge in the sword of Orion. Inside it, telescopes have revealed protostars, objects still in the process of collapsing, not yet hot enough at their cores to ignite fusion, wrapped in disks of gas and dust that may one day become planets. Some of those protostars are less than 1 million years old, infants by stellar standards, so young they have barely begun. Other galaxies have nurseries far more active than anything in the Milky Way, starburst galaxies, where entire regions blaze with newborn stars. The rate of formation so high that the galaxy consumes its gas supply in a fraction of a normal galaxy's lifetime. A maternity ward the size of a solar system, bright with the effort of beginning. New suns still forming, wrapped in the cloud they came from. Our sun was born in one of those nurseries, and it had siblings, once stars, that formed from the same molecular cloud at roughly the same time. This is not speculation, it is inferred from the chemistry. Stars born together share the same initial composition, the same ratios of elements, because they condensed from the same cloud. By measuring the chemical fingerprints of nearby stars, their ratios of particular isotopes, astronomers have identified candidates for the Sun's birth cluster. The Sun's siblings have long since scattered. The cluster dispersed over hundreds of millions of years, its members drifting apart as they orbited the galaxy on slightly different paths, diverging slowly the way handwriting diverges from a common template. Some of those stars may be within a few hundred light-years of us now. Some may be on the far side of the galaxy. Some are certainly dead. If they were massive enough, they lived fast and ended in supernovae billions of years ago. The family scattered before the Earth was old. Stars born together, now strangers across 100,000 light-years. The iron in your blood was forged in a star that died before the sun was born. This is not metaphor and not poetry, it is the established account of how iron enters the universe. Iron is not produced in ordinary stellar fusion. It is the end point of fusion in massive stars, the last element that can be fused with a net release of energy. When a massive star's core fills with iron, fusion stops. The core collapses in less than a second. The outer layers rebound in a supernova, one of the most energetic events in the universe, and the iron, along with all the elements lighter than it is, scattered into the surrounding space. That scattered material eventually mixes into molecular clouds, which eventually collapse into new stars and their planetary systems. The iron in the hemoglobin carrying oxygen through your body right now traveled that path. It was inside a star. The star exploded. The iron drifted. A cloud formed around it. The sun and earth condensed from that cloud. And here you are, with a star's final product moving through your veins. A dead star's last work still doing its job. You are not watching the galaxy from outside, you are made of it. This is the fact that changes the nature of all the others once it settles. The distinction between observer and observed, between the person looking at the galaxy and the galaxy being looked at, is not a clean line. Your body is assembled from material that was processed through galactic systems born in stars, scattered by supernovae, drifted through interstellar space, gathered into a molecular cloud, condensed into a solar system, layered into a planet arranged by chemistry, into cells assembled by evolution, into a form that can sit quietly at the end of a day and feel the weight of the universe pressing gently against it from all sides. You are not a visitor to the galaxy. You are one of the things the galaxy has made. One of the more complicated arrangements, perhaps. One of the rarer ones. But made of the same material by the same processes, following the same physics as everything else out there. The galaxy looking at itself through you. Some galaxies have no star formation at all. They are called red and dead, full of old light. The name is blunt, and that bluntness is appropriate. A red and dead galaxy has used up or lost all its cold gas, the fuel that collapses into stars. What remains is an aging stellar population. The old stars gradually cooling and shifting from white and yellow toward orange and red as they near the ends of their main sequence lives. No new stars ignite. No stellar nurseries blaze in the infrared. The galaxy holds what it has and slowly spends it. Massive elliptical galaxies, some of the largest in the universe, are often in this state. They made their stars early in enormous bursts and have been coasting ever since. From outside, they still appear luminous. Hundreds of billions of old suns are not nothing. But the light is aging light, the light of stars that formed when the universe was young, now in their long, quiet decline. Still burning. Not for much longer. Old lights still arriving from fires no longer lit. Others are starburst galaxies, forming new stars at a rate 100 times faster than the Milky Way, burning through their gas in a fraction of the time. A starburst is often triggered by an interaction, a close pass with another galaxy, or a merger, compressing gas clouds and pushing them past the threshold of collapse. The resulting burst of star formation is so intense that the energy output of the newborn stars, their light, their stellar winds, their eventual supernovae, can drive gas out of the galaxy entirely, a process called a superwind. The galaxy essentially burns its own fuel so fast that the fire blows itself out. The most extreme starbursts produce as many new stars per year as the Milky Way produces in 1,000. They blaze in infrared, brighter than almost anything else in the universe, outshining even quasars in some wavelengths. And then when the gas is gone, they go quiet. The starburst ends. The galaxy settles into something older and dimmer. The brilliant phase lasts almost no time at all. The brightest flames are always the briefest. A starburst galaxy glows so brightly in infrared that it can outshine everything around it, like a hearth throwing heat into a dark room. The comparison is imprecise in scale but accurate in feeling. A hearth warms a room not by producing visible light alone, but by radiating heat infrared that the surrounding air and walls absorb and re-radiate. A starburst galaxy does something structurally similar. The newborn stars heat the surrounding dust, and the dust re-radiates that energy as infrared light. So the galaxy that looks modest in visible wavelengths, partially obscured by its own dust, blazes in infrared, its true luminosity revealed only by instruments tuned to those longer wavelengths. The warmth is real. The fire is real. The dust is just the curtain in front of it. And on the other side of that curtain, billions of new suns are doing what suns do, burning, irradiating, warming, whatever is close enough to feel it. Behind the curtain of dust, something is very warm. The atoms in your body have each been inside a star. Not near one. Not orbiting one from a comfortable distance. Inside at the core, or at least deep within the interior, where pressures are measured in millions of atmospheres and temperatures in millions of degrees. The carbon, the nitrogen, the oxygen that make up the bulk of your body's chemistry were forged in stellar interiors through nuclear fusion. Smaller nuclei pressed together until they became larger ones, releasing energy in the process. That energy is what made the stars shine. And the product of that process, the heavier nuclei, the new elements, were eventually scattered when those stars ended. Some ended gently, as red giants shedding their outer layers into space. Some ended violently, as supernovae tearing themselves apart in seconds. Either way, the material they released drifted through interstellar space, cooled, gathered into clouds, and eventually across timescales too long to feel became you. Every carbon atom in your body has been through that process. Every oxygen atom, every nitrogen atom in your DNA. You have been inside a star. You came out the other side as this. You have been compressed and fused and scattered and then gathered again into this particular shape. The history of the matter in your body is a history of extreme states followed by quiet ones, compressed to stellar core pressures, fused into new elements, scattered at supernova velocities across light years of space, then slowed by the drag of interstellar gas, then gathered by gravity into a molecular cloud, then compressed again more gently into a protostellar disk, then accreted into a planet, then dissolved into an ocean, then incorporated into the first cells, then passed through billions of years of biological inheritance until it arrived here, arranged into a body that breathes and wonders and lies still in the dark. The matter did not intend any of this. Matter does not intend, but the sequence is real, and the sequence ends, for now, in a person who can look up and recognize the process that made them. That recognition may be the strangest thing the universe has ever produced. Scattered across a galaxy, gathered into a question. The calcium in your bones was made in a supernova, a star that ran out of fuel and gave everything outward in a single second of collapse. Calcium is not light enough to be made in ordinary stellar fusion for most of a star's life. It is produced primarily in the final rapid stages of nuclear burning in massive stars, silicon burning, a process that runs for only a day or so before the core fills with iron and the collapse begins. In that collapse, and in the rebounding shockwave of the supernova that follows, calcium is forged and flung outward into space. The calcium in your teeth, in your spine, in the small bones of your inner ear that convert sound into nerve signals, all of it took that journey. A star collapsed. The shockwave passed outward through layers of gas at a significant fraction of the speed of light. The calcium scattered into the interstellar medium. Billions of years passed. And eventually that calcium was here, in a body that uses it to stand upright. A collapsed star is what holds you up. When you breathe in atoms that have crossed galaxies before they crossed you. Not all of them, most of the oxygen you inhale formed in stars within the Milky Way. But some fraction of the interstellar medium has been enriched by material from infalling gas from the Magellanic Clouds, from ancient interactions with other galaxies. The galactic ecosystem is not sealed. Gas flows in from outside, accreted along filaments, stripped from companion galaxies captured during close encounters. Some of that gas eventually finds its way into molecular clouds, into stars, into the planets around those stars, and in some cases, into the atmosphere of a small blue planet orbiting an unremarkable star. The oxygen entering your lungs right now has a history. That history is long and not fully traceable. But it begins in some threads well outside the galaxy you were born into. You are breathing the product of a universe that does not respect the borders between galaxies any more than a river respects the borders between countries. Each breath draws in something that has traveled longer than the Earth has existed. The oxygen that enters your lungs right now was forged in a massive star that may have lived in a galaxy far older than ours. This is the further claim, the one that stretches the chain to its full length. The very early universe produced only hydrogen and helium. Oxygen required stars. The first stars, called population 3 stars, were enormous, short-lived, and formed when the universe was only a few 100 million years old. They burned hot and fast, producing heavier elements and scattering them in supernovae. Some researchers believe that oxygen produced in those first-generation stars may, through the long chain of recycling and reincorporation, have eventually found its way into the interstellar medium that seeded later star systems. If so, some of the oxygen in your lungs may have been forged in a star that no longer exists in any galaxy that still exists. A star from the universe's first chapter, in a galaxy that has since merged into something unrecognizable. The first stars are gone. Some of what they made is here, in you. Your body is not separate from the cosmos. It is a temporary shape the cosmos has taken. This is the fact that sits beneath all the others, the other facts are approaching from different directions. The boundary you feel between yourself and the rest of the universe, the skin, the temperature, the sense of being contained and individual, is real in a practical sense. It is not real in a physical sense. The atoms that constitute you are not yours. They were other things before. They will be other things after. The pattern they form, the arrangement that processes sensation and memory and breath, is temporary, as all arrangements are. Stars are temporary arrangements of plasma. Galaxies are temporary arrangements of stars. You are a temporary arrangement of atoms that have been through stars and will be through others. The cosmos is not something you are inside of. It is something you are made of continuously right now in this moment while you breathe. Not a visitor to the universe, an expression of it. Every heavy element, heavier than iron, was made in a neutron-star collision, 2 dead stars finding each other across the dark. Iron is the end of what ordinary stellar fusion can produce. Everything heavier, gold, silver, platinum, iodine, barium, uranium, requires an environment more extreme than a stellar interior. For decades, the leading candidate was supernovae. Then in 2017, gravitational wave detectors detected the merger of 2 neutron stars, and telescopes turned to the source in time to observe a kilonova, a flash of light, rich in the spectral signatures of heavy elements. Exactly as predicted. The 2 neutron stars, each one the collapsed remnant of a massive star, each one roughly the mass of the Sun compressed into a sphere 20 kilometers across, had been orbiting each other for billions of years, spiraling closer as they radiated gravitational waves, until they finally touched and merged in a phonty collision that lasted milliseconds and produced more gold than the mass of Earth several times over. 2 dead stars embraced and made everything precious. Some of that gold, that platinum, that iodine moving through your thyroid right now came from 2 neutron stars colliding in a galaxy we may never identify. The kilonova detected in 2017 occurred in a galaxy about 130 million light-years away. But the heavy elements in your body are older than that event. They were made in collisions that predated the solar system, scattered into the interstellar medium billions of years ago, incorporated into the molecular cloud that formed the Sun. Those specific collisions are not recorded anywhere we can read. The galaxies they occurred in may have since merged, changed, dispersed their stars across other structures. The heavy elements traveled without a label. They carry no record of origin beyond their atomic number, the number of protons in their nucleus set at the moment of their creation and unchanged since. Your iodine is old. Its birthplace is gone. It arrived without an address. Made in a collision billions of years ago, still doing the work it was built for. The light that strikes your closed eyelids right now has traveled some of it from sources so far that the journey took longer than the Earth has existed. Your eyelids are not dark. Even closed, they admit, light a warm red glow if the room has light, a deeper dark if it does not. Some of the photons crossing that thin membrane originated nearby. Some came from the sun, bounced off the walls, refracted through the window. But some, a small fraction, came from further. Starlight reaches through roofs and ceilings in quantities too small to perceive consciously, but real. Cosmic rays, high-energy particles, some of them from outside the galaxy, pass through your body at a rate of roughly 1 per second. The distinction between your body and the universe is, at this level of granularity, a question of what you count as arriving versus what you count as passing through. Right now, things are passing through you that began their journeys before the Earth was a planet. Even your closed eyes are not closed to the universe. You have never been in one place. Not once. Not for a single second of your life. The Earth rotates, carrying you eastward, at a speed that varies by latitude but reaches roughly 1,000 miles per hour at the equator. The Earth orbits the Sun, carrying you at about 100,000 kilometers per hour through the solar system. The Sun orbits the galactic center, carrying you at about 800,000 kilometers per hour around the Milky Way. The Milky Way moves through the local group, and the local group moves within the Virgo supercluster, and the supercluster moves within the cosmic web. These velocities stack. They do not cancel. At this moment, your body is moving through space in multiple directions simultaneously at speeds that would cross a continent in seconds, and you feel none of it. The sense of stillness you have right now, the feeling of being exactly here, exactly in this place, is real. It is just a very local description of something that is at larger scales, in constant and enormous motion, still in the only sense the word was ever meant to carry. Right now you are moving at roughly 500,000 kilometers per hour relative to the cosmic microwave background without feeling a thing. The cosmic microwave background, the faint afterglow of the Big Bang filling all of space, provides the closest thing the universe has to a fixed reference frame. When astronomers measure our velocity relative to it, they find that the Earth, carried by the Sun, carried by the galaxy, carried by the local group, is moving at about 600 kilometers per second in the direction of a region of sky near the constellation Leo. 600 kilometers per second is about 500,000 kilometers per hour. At that speed, you would cross the entire United States in roughly 15 seconds. And you are moving at that speed right now. In this room, lying still. The stillness is inside the motion. The quiet is inside the velocity. The universe is moving everything, and nothing needs to hold on. The fastest you have ever traveled is right now at rest. The Milky Way itself is being pulled gently, steadily toward a mass so large it has no common name, only a direction. Astronomers call it the Great Attractor. It sits roughly 250 million light-years away, in the direction of the Centaurus and Hydra constellations, and it exerts a gravitational pull that is drawing our galaxy and all the galaxies of the local group, and even the larger Virgo supercluster toward it at several hundred kilometers per second. The Milky Way has always been moving in this direction. Long before the first human looked up, long before the Earth formed, long before the Sun ignited from its molecular cloud, the galaxy was already drifting toward this distant concentration of mass. You were born into a trajectory that was set billions of years before your birth. The pull is gentle, imperceptible in any single lifetime, but it has been going on for a very long time, and it will continue for a very long time after. Something vast is pulling the galaxy toward it slowly without announcement. That pull is called the Great Attractor, and we are inside its influence right now, in this room, in this moment, in this body. The Great Attractor is not a single object. It appears to be a massive concentration of galaxies and dark matter, a supercluster of superclusters, a node in the cosmic web so dense that it bends the flow of everything in a vast surrounding region toward it. Our entire Laniakea supercluster, the 500 million light-year structure we live inside, is itself falling toward this attractor, the way water on a tilted surface flows toward the lowest point. Scientists still aren't entirely certain what the Great Attractor is, partly because it sits behind the thickest part of the Milky Way's dust, the zone of avoidance, where our own galaxy's plane blocks the view. We are being pulled towards something partially hidden behind our own home, and we cannot stop, and we do not need to. The pull is not danger. It is just gravity, doing what gravity has always done, drawing things across every scale quietly toward each other. You are falling slowly towards something you cannot see. Scientists still aren't entirely sure what the Great Attractor is. It lies behind the thickest part of the Milky Way's dust, hidden from our best instruments in visible light. Radio waves and X-rays pass through the dust more freely than visible light, and surveys in those wavelengths have revealed clusters of galaxies in the direction of the attractor, the Norma cluster, the Centaurus cluster, and others. But the full picture remains partly obscured. Some researchers think the Great Attractor is itself being drawn towards something even larger, the Shapley supercluster, one of the most massive concentrations of matter in the observable universe, located about 650 million light-years away. If so, we are not simply falling toward the Great Attractor. We are falling towards something else. The universe's gravitational hierarchy goes deep, each structure embedded in a larger flow, each flow embedded in a larger one, all the way up to scales where the expansion of space overwhelms gravity, and the flows dissolve into the general drift apart. A river inside a river inside a river, all moving the same way. And yet we can feel its gravity. We are moving because of something we cannot fully see toward a destination we did not choose. There is something particular in that, not troubling, just particular. Much of what shapes a life is invisible and not chosen. The conditions into which you were born, the chemistry that makes you who you are, the slow pulls of habit and affection and necessity that curve the path without announcing themselves. The Great Attractor is in this way not so different from the ordinary forces that carry a life in directions it did not plan. You did not choose to be in this galaxy. You did not choose this position in the cosmic web. You did not choose to be falling at several hundred kilometers per second toward a concentration of mass 250 million light-years away. And yet here you are, falling quietly with everything else, in exactly the direction the universe arranged for you from the beginning, carried as everything is toward something larger. The darkness between galaxies is not nothing, it hums with radiation left over from the beginning of the universe. The cosmic microwave background fills all of space. It is not localized to any region or source, it comes equally from all directions, a sphere of faint microwave radiation surrounding every observer in the universe. Equally because every observer is inside the afterglow. It was produced when the universe was about 380,000 years old, hot enough before that moment to be opaque, as dense as the interior of a star, with photons bouncing off charged particles and traveling nowhere. Then the universe cooled enough for electrons to combine with protons into neutral hydrogen atoms, and space became transparent. The photons that had been trapped were suddenly free. They streamed outward in all directions. They have been traveling ever since. They have been stretched by the expansion of space from high-energy light into low-energy microwaves. And they are here, in this room. Passing through the walls, the ceiling, you. The first light the universe ever freed is still traveling, still here. That radiation is called the cosmic microwave background, and it fills every corner of space, including this room, passing through you right now, as it has every moment of your life. Before this fact was explained to you, it was still true. The radiation was here before you knew its name. It was here when you were a child, looking at the sky and not knowing what it was. It was here before you were born. It was here before the Earth formed. It has been here since 380,000 years after the Big Bang, older than any galaxy, older than any star, older than any heavy element in your body. The universe's oldest light passes through your skin about 1 billion times per second, each photon carrying almost no energy. Each one, a messenger, from the moment the universe first became transparent. You cannot feel them individually, but they are real, and they are constant, and they have been with you every moment of your existence without ever once being noticed. The oldest thing in the universe is passing through you right now. You are bathed in the afterglow of the beginning. It passes through walls, through air, through you, without stopping, without slowing, without leaving any mark you can detect. And yet it is measurable. It has been mapped with extraordinary precision by satellites designed for exactly that purpose, and its map shows the tiny temperature fluctuations that seeded all the structure in the universe. The slightly denser regions in the cosmic microwave background became the filaments. The slightly sparser regions became the voids. The pattern in that ancient light is the blueprint of everything that came after every galaxy, every star, every planet, every living thing. The afterglow contains the faint imprint of the beginning of structure, and structure, given enough time and gravity, eventually produced the conditions for you to exist, and for you to lie still in the dark, and for the same ancient light to pass through you as it passes through everything else impartially, continuously, as it always has. The blueprint of the universe is passing through the body that resulted from it. Some galaxies are so far away that they were already old when the light we are seeing today first left them. The James Webb Space Telescope has observed galaxies that existed when the universe was only 300 or 400 million years old, a fraction of its current age. But some of those galaxies were not young when their light departed. They were already mature, already structured, already containing older stellar populations, already having cycled through at least one generation of star formation and death. They were old when the universe was young. The light from those galaxies has spent over 13 billion years in transit. The galaxy we are seeing is already old in the image. What it looks like now, what it has become in the 13 billion years since that light departed, is entirely beyond our current reach. We are receiving a message from something that was already old when it sent it, and we are only now reading it. An old letter from an old thing arriving now. That galaxy no longer looks like what we see. Time has already changed it beyond recognition. This is not a limitation of our instruments. It is a consequence of the speed of light and the age of the universe. Light is fast, the fastest thing there is, but the universe is old and the distances are large, and so every image of a distant galaxy is an image of the past. The further the galaxy, the older the image. At a distance of 13 billion light-years, the image is 13 billion years old. The galaxy in that image has had 13 billion years to change since the photograph was taken. It may have merged with others. It may have consumed dozens of smaller galaxies. Its star formation may have ended entirely, leaving it red and quiet. Its central black hole may have grown by a factor of hundreds. The living galaxy, whatever it is now, is permanently beyond our sight. We are always in astronomy, reading history. The present is the one thing we cannot see. The universe shows us only its past. Its present remains its own. In a way, every telescope is a time machine. The further it looks, the older the light, the deeper into the past it reaches. This is not metaphor. The delay is real. When you look at the sun, you are seeing it as it was 8 minutes ago, the time it takes light to cross the distance from the sun to Earth. When you look at the nearest star, you are seeing it 4 years ago. When you look at the Andromeda Galaxy, you are seeing it 2.5 million years ago. When the James Webb Space Telescope looks at the most distant galaxies, it is seeing the universe as it was 13 billion years ago. Astronomers use this not as a limitation, but as a tool. The further they look, the earlier in the universe's history they see, and by looking across a range of distances, they can reconstruct a history of galaxy formation, of star birth of the universe, assembling itself from diffuse gas into the complex structure we inhabit. The sky is not a snapshot of now. It is a record of then, at every depth, simultaneously. Look far enough, and you are watching the beginning. The James Webb Space Telescope has found galaxies so far back in time that they challenge what we thought we knew about how galaxies form. Launched in December 2021 and beginning science operations in 2022, Webb was designed to see the earliest galaxies, those that formed in the first few 100 million years of the universe's life. What it found surprised many astronomers. Galaxies that appeared too large, too bright, too structured for their age. Galaxies that contained more stars than the models said they should have been able to form in the time available. Not one or two anomalies enough that the pattern was hard to dismiss. Some researchers cautioned that the early redshift estimates might be imprecise, that the galaxies might not be quite as early as they appeared. Others began revising models, exploring whether star formation efficiency was higher in the early universe, whether dark matter clustered differently, whether something fundamental about our understanding of the first billion years needed rethinking. New eyes opened and the universe looked different than the story. Some of those galaxies are larger and more formed than they should be at that age, like finding a fully grown oak in a forest that is only a few years old. The analogy is imprecise. Forests do not grow oak trees in a few years under any conditions, while the early universe was at least capable of growing galaxies, just perhaps not this quickly. But the strangeness it points to is real. Our models of galaxy formation are built on decades of observation, simulation, and theoretical work. They are not guesses. They are detailed, tested, and generally accurate across a wide range of observations. And yet these early galaxies fall outside what those models comfortably predict. Something in the early universe, some process, some efficiency, some aspect of physics we have not fully characterized, was moving faster than expected. The universe was not reading the draft we handed it. It was already several chapters ahead. The universe ignored the timeline we set for it. Perhaps our models of the early universe are incomplete. Perhaps the universe had a different childhood than we imagined. This is not a crisis, it is science functioning as it should. Every time observations fail to match predictions, the predictions are examined, refined, or replaced. The history of cosmology is full of moments where the universe turned out to be stranger, larger, older, or more structured than the current model allowed. The expansion of the universe was not in any model until it was observed. Dark energy was not in any model until the supernovae told us it had to be. The cosmic web, the cosmic microwave background, the existence of other galaxies, each of these was at one time beyond what anyone had predicted or expected. The model catches up, it always has. But catching up requires first being surprised, and the surprise requires that the universe be the kind of place that exceeds every container we build for it. Every model is a first draft. The universe is always revising. The universe is under no obligation to match our expectations. This is perhaps the most quietly important fact in all of science, not specific to astronomy, not specific to galaxies, but demonstrated most clearly at the largest scales. Human intuition was built for a world of middle distances, things you can throw, catch, walk toward, and touch. It was not built for the scales of galaxies, or the time scales of star formation, or the physics of neutron stars, or the geometry of an expanding universe. When our intuitions fail at those scales, it is not the universe that is wrong. Our models are always approximations, always the best current description of what the data shows. The universe simply is. It was here before the descriptions. It will be here after them. And every time, it surprises us. Every telescope shows us something that doesn't fit. It is offering an invitation to a more accurate account of what it actually is. The universe has never been wrong. Only our maps have been. That is not a failure, it is an invitation. Every mismatch between prediction and observation is a door. Some doors are small, a slight discrepancy that turns out to be a measurement error, or a subtle effect already within the theory. Others are large, the kind that require dismantling a foundational assumption and rebuilding from a different floor. The anomalous galaxies found by Webb may be a small door, or they may be a large one. No one knows yet. The data is being analyzed, the models are being revised, and the conversation between observation and theory is continuing the same conversation that has been going on since the first person noticed that the sky had a pattern. What makes the invitation remarkable is not that it leads somewhere known. It leads somewhere the models haven't been. And the history of cosmology suggests that where the models haven't been is almost always stranger and more beautiful than where they have. Every wrong map is an invitation to draw a better one. Everything we know about galaxies was learned in the last 100 years, a blink of geological time, barely a breath in the life of any star. The first reliable distance measurement to another galaxy was made in 1923. Before that, the Milky Way was believed to be the entire universe. Every galaxy we have ever named, photographed, catalogued, or described, every quasar, every starburst, every radio galaxy, every gravitational lens, every cosmic web filament was discovered within a single human century. The technology that made it possible, radio telescopes, space-based observatories, digital detectors, computer simulations capable of modeling billions of particles, was developed within living memory. The science of galaxies is young. The galaxies themselves are ancient. And what we know, compared to what is there to know, is almost certainly a very small fraction. We are in the early chapters of a very long book, and the early chapters always underestimate what is still to come. 100 years of looking at a universe 10 billion years old. A century ago, we did not know other galaxies existed. We thought the Milky Way was all there was, an island universe, the sole collection of stars floating in an otherwise empty and infinite dark. The objects we now know to be other galaxies were called nebulae, fuzzy patches of light, origin unknown, debated. Some astronomers argued they were distant star systems, comparable in size to the Milky Way millions of light-years away. Others argued they were nearby clouds of gas within the Milky Way, far smaller and closer. The debate, called the Great Debate, was not resolved by argument. It was resolved by measurement. And the measurement changed everything, not just the scale of the universe, but the entire frame within which every question about the universe was being asked. Before 1923, every cosmological question was, without anyone realizing it, a question about one galaxy. After 1923, the same questions opened into a universe of hundreds of billions. 1 century ago, the universe was the Milky Way. Then it wasn't. Then Edwin Hubble measured a flickering star in the Andromeda Nebula, and the universe grew larger overnight. The star was a Cepheid variable, a type of star that pulsates with a period directly related to its intrinsic luminosity. By measuring its period, Hubble could calculate how bright it truly was. By comparing that true brightness to how bright it appeared, he could calculate its distance. The distance was far beyond the edge of the Milky Way, far enough to make the Andromeda Nebula not a nearby gas cloud but an entire galaxy, appear to our own 100 billion stars at a distance of nearly 1 million light-years. The measurement was published in 1924. The implications were immediate. If Andromeda was a separate galaxy, then the other nebulae, hundreds of them, thousands of them, were also separate galaxies. The universe was not one island. It was an ocean of islands. And we were on one of them looking out. A single flickering star, and the universe became unrecognizable. One measurement, one person, one clear night, and everything changed. This is the part of science that does not get told often enough, that behind the vast machinery of modern astronomy, behind the satellite arrays and the supercomputer simulations and the international collaborations involving thousands of researchers, there are still moments that hinge on something simple. A person at a telescope on a night with good seeing, measuring the brightness of a variable star in a photograph. Hubble was not alone. He built on the work of Henrietta Swan Leavitt, who had discovered the period luminosity relationship for Cepheid variables years earlier, working as a human computer at the Harvard Observatory. Her work made his measurement possible. Science is rarely one person and one night. But the moment of recognition, the moment when the measurement resolves into a meaning, is always specific, always small, always human in scale. A number written down that changed the size of everything. A small pencil mark. An infinite expansion of the known. There are galaxies shaped like jellyfish, long trailing tendrils of gas streaming behind them as they move through the hot plasma filling their galaxy cluster. The shape is not incidental. As these galaxies move through the cluster medium, the surrounding gas exerts a pressure on them like wind on a dandelion, stripping the outer gas away and drawing it into long filaments that trail in the direction opposite to the galaxy's motion. These tendrils can extend for hundreds of thousands of light years longer than the galaxy itself is wide. They glow in wavelengths that reveal warm hydrogen, ionized by the radiation from young stars that have ignited within the streams themselves. The jellyfish galaxy moves, and in moving leaves behind a wake that blooms with new stars. Not loss, not damage, something closer to the opposite. The stripping that should silence the galaxy instead seeds it with light, at least for a while, in the long threads it leaves behind. Moving through the dark, trailing something that glows. Those tendrils are nursery's new stars, forming in the stripped gas born in the wake of something passing. This is not what anyone expected. The gas being stripped from a jellyfish galaxy was assumed to be lost, removed from the galaxy's supply, unavailable for future star formation, dispersed into the cluster medium and eventually assimilated. But the tendrils are not passive. The gas within them is dense enough in places to collapse. And where it collapses, stars ignite small clusters of new suns, forming in threads of gas hanging in the space between the galaxy and the cluster. Stars born, in other words, outside any galaxy. Stars that belong to no disk, no arm, no structure, only to the tendril, which is itself temporary. Those stars will eventually be stripped free entirely, left as orphans in the cluster medium, or absorbed into another galaxy entirely. Born in motion, never settled, stars that will never have a home and burn no less for it. Some galaxies have rings of blue young hot stars arranged in a circle, like a crown, around an older center or a tide pool lit from within. These rings form through several mechanisms. In some cases, a smaller galaxy has passed through the center of a larger one, sending a compression wave outward through the disk, the same mechanism as the cartwheel, producing a ring of triggered star formation at the wavefront. In other cases, gas funneled inward along particular orbital resonances accumulates in a ring around the galactic center, then collapses into stars along that ring. The blue color is significant. Blue stars are young stars, hot-burning, fast-living, short lives, measured in millions rather than billions of years. Where you see blue in a galaxy, you are seeing something recent, something that has not yet had time to age. The ring of blue is a ring of newness around something old, and the contrast of that, the fresh circle drawn around the ancient center, holds its own particular quiet. New light arranged in a ring around what is very old. A galaxy called the Sombrero wears a wide, dark lane of dust across its middle, like the brim of a hat pulled low over the eyes. The Sombrero Galaxy Messier 104 is an edge-on spiral seen from the side rather than from above, so its flat disk appears as a thin line bisecting a bright central bulge. Along that disk, a prominent lane of dark dust absorbs the starlight behind it, casting a shadow across the bright core. The bulge above and below the dust lane glows with the warm, steady light of billions of older stars. The dust lane itself contains younger stars and star-forming regions hidden within the obscuring clouds. From our angle, the galaxy looks like something resting, something settled. The brim of the hat gives it a sense of gravity, of weight, of a structure that has found its shape and kept it. Some galaxies look like they are still becoming. The Sombrero looks like it arrived long ago and has been here since. A galaxy at rest, its brim pulled low, its light unhurried. Some galaxies look like they are in conversation, Two spirals positioned close together in the sky, their arms curving toward each other, the space between them threaded with faint streams of stars pulled loose by mutual gravity. The most famous pair is the Whirlpool Galaxy, and its companion a large face-on spiral and a smaller irregular galaxy caught in its gravitational influence. The smaller one sitting at the tip of one of the whirlpool's arms like a period at the end of a long sentence. The interaction has triggered star formation in both galaxies. The arms of the larger one are brighter and bluer on the side nearest its companion. The smaller one has been distorted, its original shape replaced by something asymmetric pulled toward the larger. They have not yet merged. They are still in the early stages of an encounter that will last hundreds of millions of years. Right now they simply face each other, each one altered by the other's presence, neither one yet consumed. Two galaxies changed by nearness, not yet one. The antennae galaxies have been colliding for hundreds of millions of years, and they are still in the middle of it. The two galaxies NGC 4038 and NGC 4039 began their encounter roughly 1 billion years ago, and have already passed through each other once, their cores now pulling back together for what will eventually be a final merger. The name comes from two long tidal tails of stars that extend outward from the collision zone, like the antennae of an insect, curved streams of stars pulled loose by the gravitational interaction and flung into the surrounding space. In the center of the collision, where the two galaxies are most deeply entangled, the rate of star formation is extraordinary. Thousands of new star clusters blazing into existence in a region still threaded with chaos. The collision looks violent in photographs. It looks loud, but it is happening in silence, over time scales longer than the entire history of life on Earth, one slow degree at a time. Chaos moving so slowly it looks almost like stillness. In the collision of the antennae galaxies, billions of new stars have been born, chaos arranging itself, as it always does, into something that gives off light. The star clusters forming in the collision zone are young and intensely bright, some of them among the most luminous star clusters in the observable universe, containing hundreds of thousands of stars born within a few million years of each other. Many of those stars are massive, the kind that live fast and die in supernovae, seeding the surrounding gas with heavy elements that will enrich the next generation. A galaxy collision does not simply mix two sets of stars. It reprocesses the gas, accelerates the chemical evolution of the merged system, and produces a generation of stars that would not have existed if the two galaxies had never met. The chaos is not incidental to the creation. The chaos is the mechanism. Without the collision, those billions of stars simply would not be. What tore them apart made something that could not have been made gently. The stars themselves do not collide during a galaxy merger, only the gas clouds between them compress and ignite. This fact deserves to rest a moment before the next one arrives, because it is counterintuitive in a way that rewards sitting with. Two galaxies each, containing hundreds of billions of stars, pass through each other, and not a single star strikes another. The stars are simply too far apart. Even in the densest regions of a galactic collision, the distance between stars is so vast that the probability of a direct collision is essentially zero. What does collide is the interstellar medium, the gas and dust that fills the space between stars, that has no equivalent emptiness protecting it, that gets compressed and heated and triggered into collapse. The stars drift through each other like two clouds of smoke pushed through the same space. The smoke mixes. The individual molecules almost never touch. Two crowds walking through each other and not one shoulder grazed. After the collision, calm returns. The stars settle into new orbits. The gas that was not consumed by star formation disperses or cools. The merged galaxy finds a new shape, typically an elliptical, rounder and smoother than either of its spiral parents. Its arms dissolved into a general swarm of stars, all orbiting a common center. The starburst ends. The supernovae quiet. The rate of star formation drops slowly at first, then steeply as the available gas is used up or expelled. What remains is large, luminous, and still. A new elliptical galaxy containing the stars of two former spirals, with a merged central black hole somewhere in the middle, and a long future of slow, quiet aging ahead of it. The chaos is not permanent. It is a phase, a transition between one kind of order and another. The universe is patient with its own disorder. It always finds its way back to stillness. Everything that was loud becomes eventually quiet. Gravity always finds a way towards stillness. Given enough time, it smooths everything out. This is not a poetic claim, it is what the physics shows. Gravity is attractive. It draws things together. And, drawn together things over time, settle into the lowest energy state available to them, the most stable orbit, the most compact arrangement, the shape that requires the least ongoing adjustment. A galaxy that has been through a merger will oscillate its core, bouncing its stars, sloshing for hundreds of millions of years before settling. But it does settle. A star forming from a collapsing cloud goes through a turbulent youth, jets, outflows, violent winds, before settling onto the main sequence where it will burn steadily for billions of years. Even the universe itself, in some cosmological models, tends toward a final equilibrium, maximum entropy, minimum temperature, maximum stillness. Gravity is not in a hurry, but it is relentless, and wherever it is given enough time, it produces rest. Given long enough, everything finds its quiet. There is a type of galaxy called a lenticular, neither spiral nor elliptical, sitting somewhere between the two, like a word that means something different in every language it appears in. A lenticular galaxy has the flat disk of a spiral, but none of the arms. The disk is smooth, unstructured, populated with older stars and very little gas. It looks in photographs like a spiral that has forgotten its arms, or an elliptical that chose to stay flat. How lenticulars form is still being studied. Some may be spirals that have been stripped of their gas by a dense cluster environment, leaving the disk behind, but removing the fuel for arm-tracing star formation. Others may have simply used up their gas through star formation and never developed pronounced arms to begin with. They occupy a quiet middle space, not the blazing blue of a starburst, not the warm orange of a red and dead elliptical. Something in between. The galaxy equivalent of late afternoon. Not quite one thing, not quite another. Somewhere in the middle, calm. Some galaxies have halos, vast, roughly spherical distributions of older stars surrounding the flat disk, extending far beyond the visible edges of the galaxy into the surrounding dark. These stellar halos are thought to be the remnants of smaller galaxies that were absorbed long ago, their stars, stripped from their original structures, and scattered into wide, looping orbits around the larger galaxy. The stars in a halo are old. They move slowly. Their orbits are inclined at all angles to the plane of the disk, so while the disk turns in a coherent rotation, the halo stars drift above and below it, each one following an elliptical path that may take billions of years to complete. They are the quietest population in the galaxy. No star formation, no bright young stars, no molecular clouds, just old stars widely spaced, orbiting in the vast dark beyond the disk, like the last few embers circling a fire that has burned down to nothing. Old stars, orbiting slowly far above the disk alone. Our Milky Way has one of these halos, a vast sphere of ancient stars, extending far beyond the visible disk, orbiting in wide loops that take billions of years to complete. Some of those halo stars were identified as members of cannibalized dwarf galaxies, their positions and velocities revealing the ghostly streams of former companions, the remnants of galaxies that fell into the Milky Way long before the Earth formed. The Sagittarius stream is one such remnant, a long arc of stars from the Sagittarius dwarf galaxy, winding around the Milky Way in a loop that spans much of the sky when mapped in 3 dimensions. Each pass of the dwarf galaxy through the Milky Way disk stripped more stars away, adding them to the halo. until what remains of the Sagittarius dwarf is a faint core still falling inward, still being consumed. The halo holds the record of every galaxy the Milky Way has ever absorbed, a history written in the positions of stars. The ghosts of eaten galaxies, still orbiting, still here. Some of those halo stars are among the oldest objects in the universe, nearly as old as the universe itself, formed in the very first generations of star formation. They were born when the universe was young and metal poor, before the heavy elements had been produced and scattered in abundance. They carry that origin in their chemistry, a composition so different from younger stars that astronomers can identify them through spectroscopy, reading the ratios of elements in their light, the way you might read the age of a tree in its rings. Some of these stars are over 13 billion years old. The universe is 13.8 billion years old. These stars were already burning middle-aged by their own long standards when the solar system formed. They were burning before the Earth existed. They are burning now quietly in the halo, above and below the disk, while you sleep, while the planet turns, while everything else goes on below them. Older than the Earth, still burning, still there above you right now. Those ancient halo stars were forged when the universe had barely any heavy elements. So they are made almost entirely of hydrogen and helium, the simplest substances the universe knows how to make. In the very early universe, before the first stars had lived and died, there was no carbon, no oxygen, no iron, no calcium, only hydrogen and helium in roughly a 3-to-1 ratio, left over from the first minutes of the Big Bang. The first stars formed from this primordial gas, pure, simple, containing none of the complexity that later chemistry would make possible. When those first stars died and scattered their processed material, the next generation had slightly more heavy elements, and the next, slightly more. The ancient halo stars formed early in this enrichment sequence, so early that their composition is almost primordial, made from the most basic ingredients, surviving to the present. There are stars in the sky tonight that are made of almost nothing but the simplest atoms in existence, and they have outlasted nearly everything that came after them. The simplest things made first, lasting longest. Pure, early, simple, the first things the universe ever made into light. This is what an ancient halo star represents, stripped to its essence. Before complexity, before the long chain of stellar generations that produced carbon and oxygen and iron and all the elements that make planets and oceans and living things possible. Before any of that, there was hydrogen collapsing under gravity, heating at the core, igniting fusion and producing light. Light was the first output of the universe's first structures. Not warmth, not wind, not chemical energy. Light. Photons moving outward from the core of the first star, crossing the surrounding gas, escaping into a universe that was still mostly dark. That moment, the ignition of the first star, is called cosmic dawn. We have not yet directly observed it, though the James Webb Space Telescope is looking. But we know it happened. The universe went from dark to lit, and the light that came from it has been traveling ever since, redshifted now beyond most instruments, whispering at the edge of what we can hear. The first light the universe ever made is still out there, still going. Some galaxies are so faint, they have been called ultra-diffuse. Their stars spread across a space so large that the galaxy is nearly transparent to the universe behind it. Ultra-diffuse galaxies, or UDGs, are not rare. Thousands have been found in galaxy clusters and in the field. But they are hard to see. They have the physical size of a large galaxy like the Milky Way, but a tiny fraction of the stars, so few that the average brightness per unit area is far below what any traditional survey would flag as a galaxy. They were only identified systematically in the last decade, when new wide-field telescopes with extremely sensitive detectors began sweeping large areas of sky with long exposure times. What they revealed was a population of galaxies hiding in plain sight, not in distant corners of the universe, but nearby, in well-studied clusters, missed for decades because they fell below the threshold of what astronomers were trained to look for. Large, ancient, almost invisible. Patient in the way that only very old things can be. There in every photograph, unseen for decades, waiting. They contain billions of stars but spread across a space so large that the galaxy itself looks like breath on cold glass, a faint momentary film there, and almost not there. The comparison is not arbitrary. Breath on glass is visible precisely because of contrast, the fog against the clear surface, the brief moisture against the dry air. An ultra-diffuse galaxy is visible, for the same reason a faint excess of light against the slightly darker background of empty space, detectable only when instruments are sensitive enough to measure the difference. Some UDGs are so diffuse that a single bright night sky would render them invisible. They can only be detected from dark sites with purpose-built instruments. They are among the most fragile-seeming structures in astronomy, their stars so thinly distributed that a passing galaxy could strip them apart entirely, and yet they have survived. Some of them are billions of years old, their stars slowly aging, their structure holding despite the thinness, old and quiet and barely there. A galaxy you could almost see through. Still a galaxy. Some ultra-diffuse galaxies have almost no dark matter, which is strange because dark matter is thought to be the scaffolding of every galaxy. The leading model of galaxy formation holds that dark matter halos form. First, gravity, collapsing dark matter into clumps, the clumps providing the gravitational wells that ordinary matter then falls into, forming stars and gas clouds, and eventually galaxies. Without a dark matter halo, there should be no galaxy. The ordinary matter would not have a framework to collect around. And yet some ultra-diffuse galaxies appear to contain almost no dark matter at all. Their stellar velocities are consistent with a mass very close to what the visible stars alone would produce. Some researchers think these galaxies were stripped of their dark matter through interactions with larger neighbors. Others think the early conditions of their formation were unusual. Some have proposed that the observations require revisions to our understanding of gravity itself. The galaxies exist. The dark matter does not appear to be there. The explanation is still forming. They should not exist without the scaffolding. They exist. Some researchers believe that every large galaxy contains at its center a record of its whole life encoded in the mass of the black hole sitting there. The relationship between a galaxy and its central black hole is one of the more surprising discoveries of the last few decades. The mass of the black hole correlates tightly with the mass of the galaxy's central bulge, a connection so consistent across thousands of galaxies that it cannot be coincidence. A more massive galaxy tends to have a more massive black hole, in a proportion that holds from dwarf galaxies to the largest ellipticals. This suggests that the two grew together, that the black hole and the galaxy shaped each other through feedback. When the black hole feeds, it releases energy that heats the surrounding gas, suppressing star formation. When star formation is suppressed, the galaxy grows more slowly. The galaxy in turn determines how much gas reaches the black hole, a conversation across billions of years, conducted entirely in gravity and heat. The galaxy and its heart growing together in silence. The black hole grew as the galaxy grew. They shaped each other, the largest and the smallest things in the system, locked in a relationship across billions of years. The black hole is tiny relative to the galaxy. Its event horizon for even the most massive is a pinprick compared to the disk of stars surrounding it. And yet its influence extends outward through jets, through radiation, through the heating of gas that would otherwise cool and form stars. It does not control the galaxy. But it constrains, it sets limits on how fast stars can form, on how much the galaxy can grow before its own central engine pushes back. The galaxy feeds the black hole. The black hole moderates the galaxy. The result, over cosmic time, is a structure that is more stable, perhaps, than it would be without that conversation at its center. A system that regulates itself, a balance maintained not by intention but by physics. The smallest thing at the center, the largest influence in the room. That relationship between the very small and the very large is still being understood. We have the correlation. We have the basic outlines of the feedback mechanism, but the details remain active areas of research. How exactly the energy from the black hole couples to the surrounding gas? What determines the timing and intensity of its active phases? Why the relationship holds so consistently across such a vast range of galaxy masses and types? The universe has produced a system in which a black hole the size of a solar system can regulate the star formation of a galaxy 100,000 light-years across, in which something that occupies a volume smaller than the distance between the Sun and its nearest planet can influence the fate of 100 billion stars. Scale in the universe is not a measure of importance. The smallest things can set the conditions for everything around them. The largest things can depend entirely on what happens at their center. The galaxy turns. At the center, something very small holds everything in place. Some galaxies pulse their central black hole, feeding, then settling, then feeding again, in cycles that may last millions of years, as regular in their rhythm as anything the universe produces. When the black hole is in an active phase, consuming infalling gas, powering jets, heating the surrounding medium, it is called an active galactic nucleus. The energy output during these active phases can be enormous enough to reheat the gas of an entire galaxy cluster, suppressing star formation not just in the host galaxy, but in the surrounding neighborhood. Then the fuel supply dwindles. The black hole settles. The jets fade. The core dims. The surrounding gas cools slowly over millions of years. It begins to fall inward again. And eventually the cycle repeats: a new active phase, a new burst of energy, a new suppression of cooling. Not random, not chaotic, a slow rhythm measured in millions of years that keep at the largest structures in the universe from collapsing inward under their own weight. A heartbeat, millions of years between each beat. When the black hole feeds, it is called an active galactic nucleus. When it rests, it is quiet, as our own galactic center is quiet tonight, as it has been for millions of years. Our central black hole, Sagittarius A star, is in a resting phase. The accretion disk is not glowing. The jets are not firing. Occasionally it flares a brief brightening in X-rays lasting a few hours, when a small pocket of gas or a shredded object crosses the innermost stable orbit. But these flares are minor. Compared to the luminosity of an active quasar, our galactic center is nearly silent. This quietness may be part of why complex life was able to develop in the Milky Way at all. An active galactic nucleus would irradiate the surrounding region with energies hostile to the chemistry of living things. The stillness at the center is not emptiness. It is the particular stillness that makes some things possible. The quiet at the center made room for everything around it. We live inside a quiet galaxy. The center is still. The arms turn slowly. The star formation rate is moderate, not a starburst, not a dead elliptical, but something in between, something steady. The Milky Way is not the largest galaxy, not the most luminous, not the most active. It is, in most measurable ways, ordinary, a mid-sized barred spiral. Somewhere in the middle of the galaxy, mass function forming stars at a moderate rate, with a quiet central black hole and two small satellite galaxies for company. And yet from inside it, from a small rocky planet orbiting an unremarkable star 2/3 of the way out from the center, the Milky Way is the whole sky. It is the river of light overhead on a dark night. It is the background of every star that has ever been named. It is the structure that contains every human life that has ever been lived. Ordinary from outside, everything from within. The most ordinary galaxy, the only home. Tonight, somewhere in the Milky Way, a star is being born in a cloud of gas that has never been named. In a molecular cloud in one of the galaxy's spiral arms, perhaps in Orion, perhaps in Cygnus, perhaps in a region without a common name, A pocket of gas has grown dense enough that gravity has won. The collapse has begun. It will take millions of years before the core grows hot enough to ignite fusion. The star will not announce itself. There will be no visible flash, no signal. The surrounding gas will simply begin to glow more brightly in infrared as the protostar warms it from within. In a few million years, a star will emerge from the cloud, blowing away the surrounding gas with its stellar wind, revealing itself to any telescope sensitive enough and pointed in the right direction. But right now it is still a secret. Still a cloud warming, slowly falling inward toward a light it does not yet know it is becoming. Somewhere in the galaxy, a star is becoming without knowing. And somewhere else, a star is ending, swelling outward in its final red giant phase, one last slow breath before the quiet comes. Stars do not end suddenly in most cases. They expand first, the outer layers puffing outward, as the core contracts the star, growing to tens or hundreds of times its original radius. A red giant is a star in its last chapter, its fuel nearly spent. Its surface cool and vast and luminous in a deep orange red. The star may persist in this phase for millions of years before the core finally collapses, or the outer layers are gently shed as a planetary nebula. In some corner of the Milky Way right now, a star that has been burning for billions of years is in this slow final expansion. Its planets, if it has any, are being swallowed or scorched. Its light is growing redder. Its time is growing shorter. And none of this is sad exactly, it is simply the shape that stellar lives take at their end, as reliable and unhurried as anything in nature. A star, very old, very large, very nearly done. Both things are happening right now, without announcement, without pause, without any signal reaching us to mark the moment. A star forming, a star ending. Somewhere in the same galaxy, at the same moment, in the same quiet continuity that has been running without interruption for 10 billion years. The galaxy does not distinguish between beginnings and endings. It contains both simultaneously. Always, at any given moment, stars at every stage of their lives, from the first collapse of a protostellar cloud to the last cooling of a white dwarf. Birth and death are not opposites in the galaxy. They are concurrent. They are the same process running at different phases in different locations, woven through the same structure. You are lying in a world that is inside a galaxy where both are happening right now, quietly, without your awareness, without needing it. Right now. Both. Without a sound. The galaxy does not pause for either. It continues as it always has, turning, forming, aging, drifting, unhurried by anything that happens within it. The rotation takes 225 million years. The arms take longer to form and dissolve. The stars take millions to billions of years to live their lives. Against those timescales, a star being born or dying is not an event. It is a continuous condition, the way breathing is a continuous condition, rather than a series of discrete events. The galaxy does not quicken when a star ignites. It does not slow when one goes dark. It simply continues carrying its 100 billion stars in their orbits, drifting within the local group, falling gently toward the great attractor. Turning as it has always turned on a schedule set by physics billions of years before the first living thing on Earth looked up and wondered what the light was. The galaxy has never stopped. It will not stop tonight. You are one of the rare arrangements of matter that can look up and wonder at all of this. Not the only one. Perhaps some researchers think the conditions for life are common enough in the universe that wonder in some form may be widespread, but rare certainly. The sequence that produced you the right star, the right planet, the right chemistry, the right 4 billion years of uninterrupted biological evolution is long and improbable enough that most arrangements of matter will never experience it. Most atoms in the universe are in stars or in interstellar gas, or in the vast dark of intergalactic space, none of them arranged into anything that can feel the weight of a blanket, or hear the quiet of a late room, or notice the particular quality of the dark when everything has settled. You can do those things. You are doing them now. And that capacity to be present, to notice, to sit with the vastness without needing to resolve it, is not nothing. It may be in the whole sweep of the observable universe, quite rare. Most matter never wonders. You do. And tonight the wondering is enough. You do not need to hold the size of the universe in your mind all at once. You do not need to remember the names of the galaxies or the distances or the mechanisms. The facts can go. What stays, if anything stays, is something quieter, a faint shift in the sense of scale, a loosening of the boundaries between here and out there. A feeling that the dark outside your window is not empty but full, not silent but humming, with things too large and too slow for any single life to witness fully. That is enough, more than enough. The universe has been doing this without an audience for most of its existence, and it will continue long after every audience is gone. But tonight, for a few hours, you were aware of it. You listened. The galaxy turned, and somewhere in it, without announcement, a star began, and another one ended, and you were here for the moment between them. Tonight, being here was the whole of it. The room is as still as it was when you began, and the galaxy has moved. Not enough to measure in a human life, but it has moved as it always moves, carrying you with it. Somewhere above the ceiling, above the atmosphere, above the thin blue skin of air that keeps you breathing, the halo stars of the Milky Way are orbiting in their wide, slow loops, ancient beyond imagining, made of almost nothing but hydrogen and helium burning, as they have burned since the universe was young. They do not know you are here. They do not need to. They burn regardless. Right now, jellyfish galaxies are trailing their tendrils of new stars through the hot plasma of distant clusters. The Andromeda galaxy is 4 kilometers closer to us than it was when you started listening, 4 kilometers across 2.5 million light-years of space, a distance so small against that backdrop that it means almost nothing, yet it is real, and it is constant. And it has been happening since before the first human beings stood upright and looked at the smudge in the sky, and did not yet have a word for what they were seeing. If these quiet journeys through the universe bring you something restful, something worth returning to, consider subscribing to the channel, not because the numbers matter, but because it means more people might find their way here, to this particular kind of dark where the facts are large, and the voice is soft, and there is nothing you need to do but breathe. The cosmic microwave background is passing through you right now. The oldest light in the universe, moving through the walls, through the blanket, through everything gentle, constant, unchanged, since the universe first became transparent. You are inside the afterglow of the beginning, as you have always been, as everything has always been. If you happen to still be awake, you can go ahead and watch the next video now. Otherwise, let the galaxy turn without you for a while. It knows the way. It has always known the way. And somewhere in the Milky Way tonight, in a cloud of gas that has no name, something is falling slowly inward toward the warmth it is about to become. Good night.